Imagine staring into the deepest part of space and finding something so strange, so impossible, that it defies everything we thought we knew about the universe. That's exactly what happened when astronomers discovered a black hole that shouldn't exist. According to all the rules of physics, this kind of black hole simply couldn't form, and yet, there it was. Huge, mysterious, real. Its existence isn't just surprising, it's a cosmic riddle that's forcing scientists to question the very nature of stars, gravity, and how the universe works. Before we begin today's journey, let us know where in the world you're watching from, and what time it is for you right now. Drop it in the comments below and settle in for a fascinating ride to the most mysterious object in the universe. A black hole is one of the most mysterious and powerful objects in the entire universe. It's a region in space where matter has been squeezed so tightly that it becomes incredibly dense. Because of this, its gravity is unimaginably strong. So strong, in fact, that nothing can escape it, not even light itself. That's why we call it a black hole. Once something crosses its boundary, it's gone forever. This strange idea comes from Albert Einstein's famous theory of general relativity. According to this theory, if a huge amount of mass gets packed into a small enough space, it will warp space and time so much that it forms a black hole. The outer edge of a black hole, the point where nothing can escape, is called the event horizon. If anything passes this invisible line, even light, it can never return. Even though black holes have such strong effects on things that get too close, they don't actually look special if you're just floating nearby. You wouldn't see any bumps, marks, or signs of what's inside. In fact, according to Einstein's theory, you wouldn't even notice when you crossed the event horizon, at least not at first. In some ways, a black hole behaves like a perfect black body in physics. That means it doesn't reflect any light, it just absorbs everything. But thanks to quantum physics, things get even more interesting. In the 1970s, scientist Stephen Hawking used quantum field theory to show that black holes aren't completely black after all. They actually give off a tiny bit of heat, called Hawking radiation, coming from the edge of the event horizon. But this radiation is extremely faint. For black holes formed from stars, this heat is only about a few billionths of a Kelvin, which makes it impossible for us to detect with today's technology. The idea of something in space having gravity so strong that even light couldn't escape was first thought about way back in the 18th century by John Michel and Pierre-Simon Laplace. But the first real mathematical description of a black hole came much later. In the year 1916, a German physicist named Karl Schwarzschild came up with a solution to Einstein's equations that describe this strange object. That's why the term Schwarzschild metric is used to describe it. It wasn't until 1958 that David Finkelstein explained the black hole as a region from which nothing could escape, not even light. For a long time, black holes were just seen as weird results in math, not something that might exist in real life. But during the 1960s, scientists began to realize that black holes were not just imaginary. They were actually a natural result of Einstein's theory. The first black hole that scientists were able to identify with some confidence was Cygnus X-1, discovered by several teams of researchers in the year 1971. Black holes usually form when massive stars, much bigger than our Sun, reach the end of their lives and collapse under their own gravity. After a black hole forms, it can grow even larger by pulling in gas, dust, and even other stars from its surroundings. When black holes become enormous, containing the mass of millions of suns, they are called supermassive black holes. These giants can grow by merging with other black holes, or by swallowing huge clouds of gas all at once. Scientists now believe that most galaxies, including our own Milky Way, have a supermassive black hole at their centre. We can't see black holes directly, but we can detect their presence by watching how they interact with other things. When matter falls toward a black hole, it often forms a spinning disk called an accretion disk. This disk gets extremely hot and bright because of the intense friction, and it shines brightly in many forms of light. In some extreme cases, this process creates a quasar, a glowing object so bright it can outshine an entire galaxy. Sometimes, if a star passes too close to a supermassive black hole, the star gets torn apart by the black hole's gravity. This process, called spaghettification, turns the star into long streams of hot gas that light up before vanishing inside. Astronomers can also study the orbits of stars that circle around a black hole. By carefully measuring how those stars move, they can figure out how much mass the black hole has and where it is located. This is how scientists have discovered many black hole candidates, especially in binary star systems, where one star orbits an invisible companion, a likely black hole. One of the most famous discoveries is the giant black hole at the heart of our galaxy. It's known as Sagittarius A star, written as Sagittarius A. Based on the movement of nearby stars, scientists estimate that this black hole has about 4.3 million times the mass of our Sun. A long time ago, before scientists truly understood how gravity affects light, two brilliant minds had a wild idea. What if there were stars so massive that not even light could escape them? This fascinating thought was first suggested in the late 18th century by two men working independently of each other, an English clergyman and astronomer named John Michel, and a French mathematician and physicist named Pierre-Simon Laplace. At the time, the concept of a black hole, as we know it today, did not exist. Instead, Michel and Laplace imagined enormous stars, much bigger than our Sun, but not necessarily denser. In the year 1784, Michel wrote a short letter where he tried to calculate how large such a star would have to be. He suggested that if a star had the same density as the Sun, but was 500 times its radius, its gravitational pull would be so powerful that light, which travels extremely fast, could not escape from its surface. This would make the star completely invisible to us. Even though the star wouldn't shine, Michel believed we might still detect it because of the way its gravity could tug on nearby stars. Later, in 1796, Laplace also talked about stars that might be too massive to be seen. In his book Exposition du système du monde, Explanation of the System of the World, he speculated that such a giant star might be invisible if it was large enough. When asked by fellow astronomer Franz Xaver von Zach to provide a mathematical explanation, Laplace did just that and published it in a journal edited by von Zach. At first, many scientists were intrigued by this idea of dark stars hiding in plain sight. But then, in the early 19th century, people started to understand that light behaves like a wave, not just a stream of tiny particles. This caused doubts about whether gravity could actually hold back light waves. As a result, interest in Michel and Laplace's invisible stars began to fade. Everything changed in 1915 when Albert Einstein introduced his theory of general relativity, which showed that gravity could indeed affect the path of light. Just a few months later, a German physicist named Karl Schwarzschild found a solution to Einstein's complex equations. This solution described how gravity behaves around a massive spherical object. It included a mysterious boundary where things became mathematically strange, what we now call the Schwarzschild radius. At that point, the equation suggested that space and time would behave in unusual and extreme ways. Shortly afterward, in the same year, Johannes Droste, a student of physicist Hendrik Lorentz, came up with the same solution on his own and wrote more details about it. Scientists at the time didn't fully understand what this strange boundary meant, but it was clear that something remarkable happened there. In 1924, British astronomer Arthur Eddington showed that this strange behaviour at the Schwarzschild radius wasn't a true physical singularity. It was more of a problem with the way the math was written. Later, in 1933, Georges Lemaitre proved that this singularity was only a coordinate problem, not something that actually existed in nature. In a book published in 1926, Eddington imagined what would happen if a real star had so much mass that it shrank to its Schwarzschild radius. He said that a star that massive would trap light, bend space so much it would close in on itself, and shift its light so far into the red part of the spectrum that it would disappear completely. Then came another important step. In 1931, a young Indian physicist named Subramanian Chandrasekhar used the principles of special relativity to calculate how much mass a white dwarf star could have before it became unstable. He found that if the mass went above about 1.4 times the mass of the Sun, the star would no longer be able to support itself. This limit later became known as the Chandrasekhar limit. Many scientists at the time didn't believe him. Eddington and others thought there must be some unknown force that would prevent a star from collapsing completely. In a way, they were partly right. Stars just a little heavier than that limit can collapse into neutron stars, which are extremely dense but still stable. But in 1939, American scientists Robert Oppenheimer and George Volkoff pushed the idea further. They proposed that if a neutron star was too heavy, even that wouldn't be enough to stop the collapse. They introduced the Tolman-Oppenheimer-Volkoff limit, which they estimated at around 0.7 times the Sun's mass, based on early calculations. Later studies that included the effects of the strong nuclear force revised the estimate to between 1.5 and 3 times the Sun's mass. In recent years, especially after the observation of a neutron star collision in the event called GW 170817, scientists narrowed the limit even further, estimating it to be about 2.17 times the mass of the Sun. Oppenheimer and his team also had a strange interpretation of what happens at the Schwarzschild radius. They thought that to an outside observer, time would seem to stop at the edge of the black hole. They called these objects frozen stars, because anyone watching from afar would see the star frozen in time as it collapsed. Also in 1939, Einstein himself published a paper trying to argue that black holes could not form. But just a few months later, Oppenheimer and his student Hartland Snyder published another paper titled On Continued Gravitational Contraction, using Einstein's own theory to show how a black hole could, in fact, form from a collapsing star. Their model became the first serious scientific prediction of black holes in modern physics. In 1958, physicist David Finkelstein finally described the Schwarzschild radius as an event horizon, a point of no return where anything that crosses it can never come back. He explained it as a one-way membrane. Things could go in, but nothing, not even information, could come out. Finkelstein also created a new way of looking at space and time that made it easier to understand what happens from the viewpoint of someone falling into a black hole. Around the same time, mathematician Martin Kruskal developed similar ideas, but they weren't fully understood at first. Eventually, the combined work of Kruskal and George Sikares led to the creation of new mathematical coordinates, Kruskal-Sikares coordinates, that helped scientists describe black holes from both inside and outside perspectives. The period between the mid-1960s and the mid-1970s is often called the golden age of black hole research. During these 10 exciting years, black holes and Einstein's theory of general relativity went from being fringe ideas to becoming a major focus of mainstream scientific work. During this time, scientists made several important breakthroughs in understanding black holes. In the year 1963, a mathematician named Roy Kerr discovered an exact solution to Einstein's equations that described a black hole that spins. This was a major leap forward, because most real black holes in space are expected to rotate. 2 years later, in 1965, another scientist named Ezra Newman found a solution for a black hole that not only spins but also carries an electric charge. As scientists dug deeper, a powerful idea began to take shape, known as the no-hair theorem. This theory was developed thanks to the work of physicists Werner Israel, Brandon Carter, and David Robinson. It said that if a black hole stops changing, in other words, becomes stable, it can be completely described by just 3 things: its mass, how fast it spins, called angular momentum, and its electric charge. According to this idea, black holes are very simple on the outside. No extra features or hair needed. At first, some scientists thought these strange black hole features, like their incredible density or the existence of a central singularity, were just mathematical tricks caused by oversimplified equations. In particular, 3 Russian scientists, Vladimir Belinsky, Isaac Kalatnikov, and Evgeny Lifshitz, believed that real black holes wouldn't have these singularities in most cases. They even tried to prove this mathematically. But in the late 1960s, 2 brilliant scientists, Roger Penrose and Stephen Hawking, used new mathematical techniques to prove the opposite. Singularities do appear in many real situations, not just rare or idealized ones. This was a turning point in physics. In recognition of this work, Roger Penrose was awarded half of the Nobel Prize in Physics in the year 2020. Unfortunately, Stephen Hawking passed away in the year 2018, so he could not be honoured with the prize. During this same golden age, astronomers were also making exciting discoveries. In the year 1967, scientist Anthony Hewish and Jocelyn Bell Burnell discovered mysterious, rapidly pulsing signals from space. By 1969, it was clear that these were real astronomical objects, not just theories. This discovery showed that incredibly dense stars, like neutron stars and black holes, were not just ideas on paper. They actually existed in space, encouraging scientists to take these compact objects much more seriously. Another major discovery came from observations in Greenwich and Toronto in the early 1970s. Scientists studied a mysterious X-ray source called Cygnus X-1, which had first been spotted in 1964. After years of investigation, Cygnus X-1 became the first object in the universe that was widely accepted to be a real black hole. At the same time, in the early 1970s, researchers such as James Bardeen, Jacob Bekenstein, Brandon Carter, and Stephen Hawking laid the foundations for a fascinating new field called black hole thermodynamics. This area of study looked at black holes in a completely new way, by comparing them to everyday physics, like the laws of heat and energy. They found deep connections. A black hole's mass is like energy, its surface area is like entropy, a measure of disorder, and its surface gravity is like temperature. Then, in the year 1974, Stephen Hawking took this idea even further. Using the laws of quantum physics, he showed that black holes aren't completely black after all. They actually give off a faint glow of energy, now known as Hawking radiation. This discovery shocked the world because it meant that black holes can slowly evaporate over time. More recently, on the 11th of February 2016, the LIGO and Virgo collaborations announced something historic. For the first time ever, they had directly detected gravitational waves, tiny ripples in space and time caused by the merging of two black holes. This discovery confirmed a key prediction of Einstein's theory, and opened up a whole new way of studying the universe. Then, on the 10th of April 2019, another incredible milestone was reached. Scientists shared the first ever image of a black hole, taken by the Event Horizon Telescope in 2017. This image showed the glowing edge of the giant black hole at the centre of the galaxy Messier 87, over 50 million light-years away. More discoveries are still happening. Observations from the Gaia space mission revealed a black hole called Gaia BH1, which lies about 1,560 light-years away from Earth. This black hole seems to have a Sun-like star orbiting it. Another black hole, Gaia BH2, may have a brown dwarf orbiting it. Even though we've only identified a few dozen black holes in our Milky Way galaxy, scientists believe that there could be hundreds of millions more. Most of them are probably quiet and alone, not pulling in matter or emitting radiation. These hidden black holes could only be detected through their gravity, by how they bend light from distant stars, a phenomenon called gravitational lensing. A black hole is an object in space where gravity is so strong that nothing, not even light, can escape from it. This is because the speed needed to escape its pull is faster than the speed of light, which is the fastest anything can travel in the universe. Scientists use a more technical way to describe a black hole. They say it's any object whose mass is squeezed into a space smaller than its Schwarzschild radius, a special size limit predicted by the math of Albert Einstein's general theory of relativity. This means if something is heavy enough and compact enough, it becomes a black hole. Once a black hole has formed and settled into a stable state, scientists believe it can be completely described by just three features: its mass, how much matter it contains, its electric charge, and how fast it spins, called angular momentum. This idea is known as the no-hair theorem. It suggests that black holes are bald in a sense. They have no other features or hair that make them different. So if two black holes have the same mass, charge, and spin, they are completely identical. They can't be told apart no matter what created them or what fell into them. However, scientists still don't know if this is entirely true in the real world, since it's a big mystery that modern physics hasn't fully solved yet. What makes these three properties special is that they can be detected from outside the black hole. For example, if a black hole is electrically charged, it can push away or pull in other charged objects, just like any other charged object in space. Similarly, scientists can measure the total mass of a black hole from far away by using gravity-based methods, such as something called ADM mass. The spin of the black hole can also be detected from a distance by watching how it twists nearby space and time, a weird effect predicted by general relativity, known as the Lenz-Thirring effect. But here's something strange. When something falls into a black hole, all details about that object, its shape, its structure, where its electric charges are, get spread out evenly over the surface of the black hole's boundary, called the event horizon. All that information is lost to the outside world. It's as if the black hole erases the details. Scientists compare the behavior of this surface to a stretchy sheet with electrical resistance and friction, kind of like rubber that also conducts electricity. This idea is called the membrane paradigm. It's very different from how normal forces like magnetism or light work, because those forces don't have friction and don't forget information. But black holes do, which leads to one of the greatest puzzles in physics, the black hole information loss paradox. This paradox is about how black holes forget things. Once a black hole reaches its stable state, with just mass, charge, and spin, it no longer shows any sign of what it swallowed. That includes tiny details that can't be measured from far away, like how many protons or electrons went into it. These are things known as quantum numbers, and normally they're preserved in physical processes, but black holes seem to break that rule, and scientists still don't know why. The simplest kind of black hole only has mass. It doesn't have any charge or spin. These are called Schwarzschild black holes, named after the German physicist Karl Schwarzschild, who discovered the mathematical solution in the year 1916. According to a rule called Birkhoff's theorem, these black holes are perfectly spherical and are the only ones that behave like this in empty space. In fact, from far away, their gravity is no different from the gravity of any other round object of the same mass. So the popular idea that black holes suck in everything is only true when you get close to them. From a distance, they behave just like stars or planets of the same weight. There are more complex kinds of black holes too. If a black hole doesn't spin but has an electric charge, it's described by what's called the Reissner-Nordström metric. If it spins but has no charge, it follows the Kerr metric. And if it has both spin and charge, it's described by the most complete solution we know so far, called the Kerr-Newman metric. Now, while a black hole's mass can be any positive number, the charge and spin can't be just anything. They're limited by the mass. If a black hole has the maximum allowed amount of charge or spin for its mass, it's called extremal. There are some strange theoretical solutions to Einstein's equations where a black hole goes beyond this limit. But those don't have an event horizon. They expose their core singularity to the universe, which scientists call a naked singularity. This is considered impossible in reality, according to something called the cosmic censorship hypothesis. This idea says the universe hides all singularities behind event horizons, and computer models and simulations seem to support this. Because the force of electricity is so much stronger than gravity, stars that collapse into black holes are expected to stay nearly neutral. They don't keep much electric charge. But rotation is another story. Most compact cosmic objects like neutron stars and black holes are expected to spin. For example, there's a black hole candidate called GRS 1915+105. It's part of a binary X-ray system and appears to spin very, very fast, close to the maximum speed allowed. Black holes are usually sorted based on their mass, no matter how fast they spin. The size of a black hole is directly related to its mass. This size is measured by the radius of its event horizon, the Schwarzschild radius. The most important feature of a black hole is this event horizon. It's a one-way boundary in space. Once something passes through it, it can never come back, not even light. That's why we say black holes trap everything. If something happens inside the event horizon, no signal from that event can reach the outside world. From our point of view, it's as if the event never happened. Einstein's theory of general relativity also says that anything with mass bends the fabric of space and time. The more mass something has, the more it warps this fabric. Near a black hole, the warping becomes extreme. At the event horizon, the warping is so strong that nothing, not even light, can escape. Here's an interesting thought experiment. Imagine an observer floating far away from a black hole watching a clock near the event horizon. That clock would seem to tick slower and slower as it gets closer to the black hole. This strange effect is called gravitational time dilation. If something falls toward the black hole, it appears to move slower and slower, as if it's frozen in time at the edge. From far away, it would look like the object takes forever to fall in. Also, the light coming from the object would get stretched out and dim, becoming redder and harder to see. Eventually, it would fade completely. This might sound like a slow process, but in most cases, the object vanishes from sight in less than 1 second. But here's the twist. If someone could fall into a black hole without being destroyed, a purely imaginary scenario, they wouldn't notice anything strange when they crossed the event horizon. Their own clocks would tick normally, and they wouldn't feel anything unusual at that exact point. This is because, in Einstein's theory, you can't tell when you cross the horizon just by using local measurements. This idea comes from what's known as the equivalence principle. However, the shape of the event horizon is always round when a black hole is not spinning. If it does spin, the shape gets slightly squashed, wider around the middle and flatter at the poles like a spinning planet. But no matter what, the horizon always forms a closed surface around the black hole. At the very heart of a black hole, according to the basic and idealized Schwarzschild model, is something incredibly strange and mysterious. A gravitational singularity. This is a region where space and time become so warped and twisted by gravity that their usual rules completely break down. In this place, the curvature of space-time becomes infinite, meaning it bends beyond any imaginable limit. If the black hole is not spinning, then the singularity is squeezed into a single point with no width, no depth, and no height, literally zero volume. But if the black hole is rotating, then this central singularity stretches into a thin, ring-shaped structure that lies flat, spinning in the same direction as the black hole itself. Despite having zero volume, this strange region holds all the mass of the black hole. That means it has infinite density, an unimaginable amount of matter crammed into a space so small that it can't even be measured. Now, the Schwarzschild model, which describes a non-spinning, uncharged black hole, is not accurate when it comes to what exactly happens right at the singularity. But one thing is clear. Anyone who falls into a Schwarzschild black hole and crosses the event horizon, the invisible boundary around the black hole, has no way to escape. No amount of effort or rocket power can save them. They can slow down their fall for a while by firing rockets in the opposite direction, but they can't stop the inevitable. As they get closer to the center, they would experience a bizarre and terrifying process called spaghettification, or sometimes jokingly, the noodle effect. This happens because the gravitational pull at their feet would be far stronger than at their head, or vice versa, stretching their body into a long, thin string. Eventually they would be crushed into the singularity, their mass becoming part of the black hole. However, not all black holes are that simple. If a black hole is either spinning, called a Kerr black hole, or has an electric charge, called a Reissner-Nordström black hole, then things get even stranger. In those cases, there might be a way to avoid the singularity altogether. Some theories suggest that if you extend the math as far as it could go, it might be possible to pass through the black hole and come out the other side, into a completely different region of space, or maybe even into another universe. In this idea, the black hole acts like a tunnel, or wormhole. But hold on. Before packing your bags for another universe, there's a catch. Any small disturbance, like even a tiny particle falling in, would ruin this delicate structure. So for now, it's just a theoretical dream. In fact, some mathematical models of spinning black holes even allow for closed time-like curves, which means you could theoretically go back in time. But this leads to strange problems like the famous grandfather paradox. What happens if you go back and accidentally prevent your own birth? Most scientists believe that these strange effects won't actually exist once we have a full, working theory that combines both quantum mechanics and general relativity. That's because singularities, those infinitely dense points, are actually signs that general relativity, Albert Einstein's great theory of gravity, is no longer enough on its own. Where matter is packed together so tightly, the rules of quantum physics must also come into play. But so far, no one has been able to combine gravity and quantum mechanics into one single theory. Scientists are working on this challenge, hoping to create a theory of quantum gravity, which might explain black holes in a way that avoids the strange and scary idea of singularities. Now let's talk about another fascinating region near a black hole, the photon sphere. This is a spherical zone just outside the event horizon where light itself can be trapped in a circle around the black hole. For a black hole that is not spinning, the photon sphere lies at a distance that is 1.5 times the Schwarzschild radius, the size of the event horizon. Photons or light particles can orbit the black hole in this zone, but it's a very unstable place. Even a tiny disturbance, like another particle or a little nudge, can send the photon flying off. It might spiral inward and get swallowed by the black hole, or it might shoot outward and escape. Any light that we see from near the photon sphere must have come from just outside it, because anything falling in from beyond that point cannot turn back. If the black hole is spinning, then things get more complicated. The shape and size of the photon sphere change depending on how fast the black hole spins and the direction in which the light orbits. Light can orbit in the same direction as the black hole's spin, called prograde, or in the opposite direction, retrograde, and that affects how close the photon can get. Spinning black holes also have another fascinating region around them called the ergosphere. This is an area just outside the event horizon, where the fabric of space-time is being dragged along by the spinning black hole. This strange effect is predicted by general relativity and is called frame dragging. In the ergosphere, standing still is impossible. Everything is forced to move in the direction the black hole spins. To stay still, an object would have to move faster than light in the opposite direction, which is impossible. The ergosphere touches the event horizon at the black hole's poles, but stretches much farther out around the equator. Interestingly, even though you can't stand still in the ergosphere, you can escape from it. In fact, there's a way to take advantage of the black hole's rotation to gain energy. This trick is called the Penrose process. If you throw something into the black hole in just the right way, the object can break into two pieces. One falls in, and the other escapes with more energy than it had before. That extra energy comes from the black hole's spin, so over time, the black hole's rotation slows down. A more powerful version of this, called the Blandford-Znajek process, happens when strong magnetic fields are involved. This may explain the powerful jets of energy and particles that shoot out from the centers of galaxies, called quasars and active galactic nuclei. Another important idea in the study of black holes is the innermost stable circular orbit, or ISCO. In regular Newtonian gravity, objects can orbit around another object at almost any distance. But near a black hole, this isn't true. There is a limit. Get too close, and your circular orbit becomes unstable. If you go just a little bit inward from this point, you will start spiraling into the black hole and won't be able to escape. How close this innermost stable orbit is depends on how fast the black hole spins. The faster it spins, the closer you can orbit safely. However, there is one last region called the plunging region. Once something reaches this zone, no matter how hard it tries, it can no longer stay in orbit. It will fall straight toward the black hole at nearly the speed of light. There is no turning back from this point. It's a one-way trip into darkness. Because black holes are so strange and extreme, many scientists once wondered whether they could really exist in nature, or if they were just strange, unrealistic solutions that came out of Einstein's mathematical equations. Even Albert Einstein himself didn't believe black holes could form. He thought that when a star collapsed, the spinning motion, or angular momentum of the particles inside it, would prevent total collapse by stabilizing them at a certain distance. This idea led many scientists working in the field of general relativity to ignore other theories that suggested black holes might be real. Still, a small group of researchers strongly believed that black holes were more than just mathematical curiosities. They were real objects that could actually form in space. By the late 1960s, they had convinced most experts in the field that nothing in Einstein's theory actually prevents a black hole from forming. In other words, there was no reason a real event horizon, the point of no return, couldn't exist. Not long after that, a scientist named Roger Penrose proved something even more incredible. Once a black hole forms an event horizon, Einstein's theory of general relativity says that a singularity, a point where gravity becomes infinite, must exist inside it, unless quantum physics somehow prevents it. Soon afterward, Stephen Hawking showed that many descriptions of the Big Bang also included singularities, even without using any strange or exotic kinds of matter. During this time, other discoveries made black holes seem much simpler and easier to understand than scientists had expected. For example, the Kerr solution, describing rotating black holes, the no-hair theorem, which says black holes can be described by just a few basic properties, and the new laws of black hole thermodynamics all helped scientists realize that black holes weren't so mysterious after all. They were real, physical objects, and very important ones. The most common way a black hole forms is through gravitational collapse, which happens when something's own gravity pulls it in so strongly that nothing can hold it up anymore. This often occurs with massive stars. As a star runs out of nuclear fuel, the stuff that keeps it burning and hot, it can no longer resist its own weight. If the star doesn't get hot enough to balance itself, it starts to collapse. Sometimes this collapse is stopped by something called degeneracy pressure, a kind of resistance created by the particles inside the star. This can lead to the creation of extremely dense objects known as compact stars. What type of compact star forms depends on how much mass is left in the star's core after its outer layers are blown away in an explosion, such as a Type II supernova. Usually the leftover core, called a remnant, is much smaller in mass than the original star. However, if the remnant weighs more than about 3 to 4 times the mass of our Sun, a value known as the Tolman-Oppenheimer-Volkoff limit, then not even neutron degeneracy pressure is enough to stop the collapse. If the original star was more than about 20 times the mass of the Sun, it could leave behind a remnant heavier than 5 solar masses, which would collapse into a black hole. These are called stellar mass black holes, and they are believed to be formed through this process. But in the early universe, things were very different. There might have been stars much bigger than anything we see today. These early monsters could have collapsed into black holes weighing up to 1,000 solar masses. These large black holes may have become the seeds from which supermassive black holes, millions or even billions of times heavier than the Sun, grew in the centers of galaxies. Some scientists believe that even larger black holes weighing as much as 100,000 suns could have formed in the young universe not from stars at all, but directly from giant clouds of gas collapsing under their own gravity. These black holes might have been the starting point for the first quasars, which are extremely bright and powerful objects we can now observe from a time when the universe was less than 800 million years old. Even though most of the energy from a collapsing star is released very quickly, things look very different to a distant observer. If you were far away watching a star collapse into a black hole, you would never actually see the moment the event horizon forms. Thanks to something called gravitational time dilation, the light from the star appears to slow down and stretch out. The star looks dimmer, redder, and slower, almost as if it freezes in time just above the event horizon and eventually disappears from view. For gravitational collapse to happen, the material involved must be extremely dense. In today's universe, such extreme density usually only exists inside stars. But just after the Big Bang, the entire universe was filled with extremely dense matter. However, density alone wasn't enough to form black holes. The mass had to clump together, and for that to happen, the early universe needed tiny irregularities or fluctuations in density. If certain areas were just a little denser than others, they could grow under gravity and possibly form primordial black holes. Different theories about the early universe make different predictions about the size of these early black holes. Some say they could be as tiny as the Planck mass, which is extremely small, while others suggest they might have been as big as hundreds of thousands of suns. Even though the early universe was very dense, it didn't collapse into one giant black hole. That's because the universe was expanding so fast that gravity couldn't pull everything back together. According to inflation theory, the early universe expanded incredibly quickly, and the effects of this rapid expansion overcame the gravitational pull. The usual models of how stars collapse to form black holes don't fully apply to the Big Bang, because the entire universe was expanding rapidly at that time. But interestingly, gravitational collapse might not be the only way to make a black hole. In theory, black holes could also form when particles collide with extremely high energy and become incredibly dense, just like in the center of stars. But as of the year 2002, no such black holes have been seen in any particle accelerator experiments, not even as tiny imbalances in the measurements. This suggests there might be a minimum possible mass for black holes to form. Scientists think this minimum might be around the Planck mass, where quantum physics becomes very important, and Einstein's theory doesn't work well anymore. That would mean we can't create black holes with any Earth-based experiment, no matter how powerful. However, some newer theories, including ideas from quantum gravity and brane-world models, suggest that black holes might form at lower energies, perhaps even at around 1 tera electron volt. If those ideas are right, then it might be possible for tiny black holes to be created naturally when cosmic rays smash into Earth's atmosphere, or maybe even in particle accelerators like the Large Hadron Collider at CERN. But most experts think this is extremely unlikely, and even if such micro black holes were created, they wouldn't last long at all. According to theory, they would vanish almost instantly, within about 10 to the power of negative 25 seconds, by giving off radiation and evaporating completely. So even if we did make them, they wouldn't be dangerous. Once a black hole has been formed, it doesn't just stop there, it can keep growing bigger and heavier. This happens when the black hole pulls in more material from its surroundings. For example, it can slowly swallow up gas and clouds of interstellar dust that drift too close. Over long periods of time, this steady eating process might be one of the reasons why some black holes grow into supermassive giants. These supermassive black holes, which weigh millions or even billions of times more than our Sun, are still a mystery to scientists, and how exactly they form is still a big question in astronomy. A similar idea has been proposed for the birth of intermediate-sized black holes, those that are not as huge as supermassive ones but are still much bigger than the regular black holes formed from dying stars. These intermediate mass black holes are thought to possibly form in dense star clusters, called globular clusters, through this same process of slowly gathering up matter. Black holes can also grow by joining with other objects. For instance, a black hole might collide with a nearby star or even with another black hole. These dramatic cosmic mergers are especially important when we think about the early universe. Back then, it is believed that many small black holes might have come together, bit by bit, forming much larger ones. Some scientists think this might also help explain where intermediate-sized black holes came from. Now let's dive into something even more fascinating. In the year 1974, the famous scientist Stephen Hawking made a groundbreaking prediction. He said that black holes are not completely black or silent as many had thought. Instead, they actually give off tiny amounts of heat and light, something now called Hawking radiation. Using the rules of quantum physics and applying them to the edge of a black hole, Hawking showed that black holes should slowly emit particles in a way that mimics the glow of a perfectly heated object, what scientists call a black body spectrum. Since Hawking first published his theory, many other physicists have double-checked his calculations using different methods, and the results keep confirming his idea. According to the theory, as black holes give off this radiation, they also slowly lose mass. Over incredibly long periods of time, they could actually shrink and eventually vanish completely. The amount of radiation a black hole emits is linked to how strong its gravity is at the surface, what's called its surface gravity. For a type of black hole called a Schwarzschild black hole, the surface gravity gets weaker as the black hole becomes more massive. That means the bigger the black hole, the less radiation it gives off. For example, a typical black hole formed from a star, let's say one with the same mass as our Sun, would have a Hawking temperature of about 62 nanokelvins, which is unimaginably cold. This is much colder than the cosmic microwave background, the faint leftover glow from the Big Bang, which has a temperature of around 2.7 kelvins. Because of this, stellar mass black holes actually absorb more heat from space than they release through Hawking radiation. So instead of shrinking, they will continue to grow over time. In order for a black hole to be warmer than the cosmic microwave background and begin to shrink from Hawking radiation, it would need to be incredibly tiny, smaller than the Moon. A black hole like that would be less than 1/10 of a millimeter wide. That's about the thickness of a human hair split 10 times. Things get even wilder when we talk about very small black holes. As they get smaller, the radiation becomes much more intense. A black hole with the same mass as a car would be smaller than a single atom, about 10 to the negative 24 meters in diameter, and it would completely evaporate in just 1 nanosecond. During that final moment, it would shine brighter than 200 suns. If a black hole had a mass of only 1 tera electron volt, which is very small by cosmic standards, it would vanish in less than 1/trillionth of a trillionth of a trillionth of a second. That is, in under 10 to the power of negative 88 seconds. For black holes this tiny, the normal laws of physics break down, and quantum gravity, an area of physics we're still trying to fully understand, might become important. Some scientists wonder if quantum gravity might allow these ultra-small black holes to become stable and stop shrinking. However, as of now, no theory has clearly shown this to be true. The Hawking radiation given off by regular black holes is extremely weak, so weak in fact that it's almost impossible to detect from Earth. But there's one exception that scientists are still hunting for: the final, explosive death of tiny black holes that might have formed shortly after the Big Bang, called primordial black holes. These miniature black holes, if they exist, could end their lives in a huge burst of gamma rays. Scientists have searched the skies for such flashes, but none have been found so far. These failed searches have helped set strict limits on how many primordial black holes might exist. NASA's Fermi Gamma Ray Space Telescope, which was launched in the year 2008, is still scanning the sky in hopes of catching one of these mysterious bursts. If Hawking's idea about black hole evaporation is correct, then a black hole with the same mass as our Sun would take about 10 to the power of 64 years to completely evaporate. But it wouldn't even start shrinking until the universe itself gets colder than the black hole. Now imagine a black hole 100 billion times heavier than our Sun. That's a supermassive black hole. It would take about 2 times 10 to the power of 100 years to disappear. And if galaxies merged into gigantic clusters, and the black holes at their centers merged as well, they could grow even larger, maybe as massive as 10 to the power of 14 suns. Even those monsters would eventually evaporate, though it would take as long as 10 to the power of 1006 years. That's a number so big, it stretches beyond our imagination. Cygnus X-1 is one of the most famous cosmic discoveries in the history of astronomy. This powerful source of X-rays is found in the constellation Cygnus, which is also known as the Swan. What makes Cygnus X-1 so special is that it was the very first object in the galaxy to be widely accepted as a black hole. Its discovery opened the door to a new understanding of the universe. The story began in the year 1964, when scientists launched a rocket to observe the sky beyond Earth's atmosphere. During that mission, they detected incredibly strong X-rays coming from the direction of Cygnus. This strange signal quickly caught the attention of astronomers because it was one of the strongest X-ray sources ever seen from Earth. The X-ray signal had a peak power density of about 2.3 times 10 to the negative 23rd watts per square meter per hertz, or, more simply, around 2,300 Janskis. Today, Cygnus X-1 remains one of the most closely studied objects of its kind. At the center of this system lies a mysterious, incredibly dense object with a mass estimated to be about 21 times greater than the mass of our Sun. This object is far too small to be any type of normal star, and its extreme properties match only one known kind of thing: a black hole. If this is true, then its event horizon, the invisible boundary around the black hole, would have a radius of no more than 300 kilometers. That's the maximum size scientists can calculate based on extremely short X-ray flashes that last just 1,000th of a second. Cygnus X-1 is actually part of a binary system, a pair of objects bound together by gravity. The second member of this cosmic duo is a massive blue-coloured supergiant star. Together they form what's called a high-mass X-ray binary system. This extraordinary pair lies around 7,000 light-years from Earth. The distance between the two members of this system is only about 1/5 the distance from the Earth to the Sun, which is roughly 0.2 astronomical units. The giant star sends out powerful winds filled with gas, and some of this material gets pulled in by the black hole. The gas forms a spinning disk around the black hole called an accretion disk. As the gas spirals inward, it heats up to temperatures of millions of degrees and gives off powerful X-rays. In addition, 2 thin, high-speed jets of energy shoot out from the disk in opposite directions, sending material far into space. Scientists believe that Cygnus X-1 may be part of a nearby group of massive young stars known as Cygnus OB3. If this connection is correct, then the system is about 5 million years old. The black hole likely formed from a massive star that originally weighed more than 40 times the mass of the Sun. This giant star lost most of its mass through stellar winds, and may not have exploded in a dramatic supernova. Instead, it may have quietly collapsed straight into a black hole. The fame of Cygnus X-1 also reached beyond the world of science. In the year 1975, two renowned physicists, Stephen Hawking and Kip Thorne, made a friendly wager about its true nature. Hawking bet that it wasn't a black hole, even though he hoped to be proven wrong. In the year 1990, Hawking admitted defeat, as the evidence overwhelmingly supported the idea that Cygnus X-1 is, indeed, a black hole. The visible star in the system, named HDE 226868, is a supergiant on its own but could not possibly produce the observed X-rays by itself. This led astronomers to suspect the presence of a hidden compact companion. In the year 1972, Louise Webster and Paul Murdin from the Royal Greenwich Observatory, along with Charles Thomas Bolton from the University of Toronto's David Dunlop Observatory, independently confirmed the existence of this mysterious object. They studied the light spectrum of HDE 226868 and noticed it was shifting slightly in wavelength. This phenomenon, called Doppler shifting, revealed that the star was wobbling due to the gravitational pull of a massive unseen companion. Using this data, scientists estimated the companion's mass and concluded that it could not be a neutron star because it was far too massive. The only explanation left was that it had to be a black hole. By the end of the year 1973, most astronomers agreed that Cygnus X-1 was very likely a black hole. Later studies showed that the system's X-ray brightness could change in as little as 1 millisecond, just 1,000th of a second. This matched predictions for a swirling accretion disk around a black hole. Some X-ray bursts lasted about 1/3 of a second, which fits with the time it would take for matter to fall into a black hole. Since then, Cygnus X-1 has been observed using a wide range of instruments both on Earth and in space. The similarities between systems like Cygnus X-1 and the powerful cores of distant galaxies, known as active galactic nuclei, suggest that they might work in similar ways. This has led scientists to place Cygnus X-1 in a special category called microquasars. These are smaller versions of quasars, the brilliant and energetic objects at the centres of galaxies, all powered by black holes, accretion disks and jets. The black hole and the supergiant star orbit each other once every 5.6 days. From Earth's point of view, the black hole never passes directly behind the star, which means the system doesn't eclipse. Scientists are still figuring out the exact tilt of the orbit, with estimates ranging from 27 to 65 degrees. In the year 2007, one study guessed the tilt to be around 48 degrees, with a margin of error of about 7 degrees. This measurement supports the idea that the two objects are separated by about 1/5 of the Earth-Sun distance. Their orbit is nearly circular, with a tiny eccentricity of about 0.018. Looking far ahead, scientists predict that in about 5 billion years, the supergiant and black hole may eventually merge into one larger black hole, possibly releasing powerful ripples in spacetime called gravitational waves. Both HDE 226868 and Cygnus X-1 appear to be travelling through space together with the Cygnus OB3 group, which lies about 7,000 light-years away. This strongly suggests that all of them were born in the same stellar nursery around 5 million years ago. The star HDE 26868 is currently located about 60 parsecs, or roughly 200 light-years, from the centre of the Cygnus OB3 group, a distance it could have travelled in about 7 million years, matching the estimated age of the group. The distance to Cygnus X-1 has been calculated in two different ways. Using trigonometric parallax, it was estimated at about 1,860 parsecs, which is roughly 6,070 light-years. Another method, called radioastrometry, gave a distance of around 2,220 parsecs, or about 7,240 light-years. In terms of its location within our galaxy, Cygnus X-1 lies along the Orion Spur, the same spiral arm of the Milky Way where our own Sun is located. It is also very close to the Sagittarius arm, another large structure of stars and gas. Some scientists even consider Cygnus X-1 a part of the Sagittarius arm, though the exact layout of the Milky Way is still being worked out. Astronomers have used different methods to measure the mass of the mysterious supercompact object at the heart of Cygnus X-1. No matter which method they used, they all seem to agree on one thing. The object is far too massive to be a neutron star. That's a strong clue that we're dealing with a black hole. Early models of how stars evolve suggested that this object might weigh about 20 times as much as our Sun, give or take 5 solar masses. Other techniques gave a more modest estimate of about 10 times the Sun's mass. But by studying the flickering X-ray signals coming from the area, scientists were able to make a more precise estimate, about 14.8 solar masses, with a possible error of just 1 solar mass. All these different values still pointed to the same conclusion. This object is most likely a black hole, a place in space where gravity is so powerful that nothing, not even light, can escape from it. The invisible edge that marks the point of no return is called the event horizon. For Cygnus X-1, this event horizon is thought to be about 44 kilometers wide. Anything that crosses it, whether it's light, gas, or even whole stars, can never come back out. In the year 2021, new measurements gave a slightly higher mass, about 21.2 solar masses, with an uncertainty of plus or minus 2.2. Then, in the year 2025, another study suggested a mass of about 17.5 solar masses, though that might just be an upper limit. Yet another method gave a similar result of 13.8 times the Sun's mass. Back in the year 1992, scientists might have caught a glimpse of the black hole's event horizon using ultraviolet light, thanks to the high-speed photometer aboard the Hubble Space Telescope. As glowing chunks of matter spiraled into the black hole, their light appeared stretched out with longer wavelengths. This effect, called gravitational redshift, was exactly what Einstein's theory of general relativity predicted. If these clumps had crashed into something solid, they would have given off a final bright burst of energy. But they didn't. Instead, 2 strange patterns of fading pulses, called dying pulse trains, were detected. That's a strong hint that these clumps vanished beyond an event horizon, exactly as expected for a black hole. For a long time, scientists weren't sure whether the compact object was spinning or not. Data from NASA's Chandra X-ray Observatory once suggested it wasn't rotating much at all. But then, in the year 2011, fresh evidence showed that it might actually be spinning at an incredible speed, about 790 times every single second. Cygnus X-1 is part of a group of stars known as the Cygnus OB3 Association. The biggest star in that group weighs about 40 times as much as our Sun. Because heavier stars burn through their fuel faster, this suggests that the star which collapsed into the Cygnus X-1 black hole must have been even more massive, perhaps over 40 solar masses. That means it lost more than 30 solar masses of material before collapsing. Some of that mass may have been transferred to its companion star HDE 226868, while the rest was likely blown away in fierce stellar winds. Interestingly, the outer layers of HDE 226868 contain extra helium, which may be leftover material from that earlier mass exchange. The original star may even have gone through a Wolf-Rayet phase, a late stage of evolution where the star sheds huge amounts of gas through powerful winds. Usually, when a massive star dies, it explodes as a supernova. But if that had happened here, the resulting explosion would likely have thrown the black hole out of its orbit. Since it remained in place, scientists believe the star may have skipped the explosion altogether and collapsed directly into a black hole, or at most caused only a small, quiet explosion. Around the black hole there's a thin, flat ring of matter called an accretion disk. This disk is made of gas spiraling inward, getting superheated by friction as it falls. The inner part of the disk is extremely hot and full of ionized particles, forming a state of matter called plasma. The outer part is cooler and stretches out to about 15,000 kilometers, about 500 times the size of the black hole's event horizon. Cygnus X-1 is one of the brightest sources of high-energy X-rays in the sky. These X-rays, which carry energies ranging from about 30 to several hundred kilo electron volts, are produced when lower energy photons are supercharged. This happens in 2 ways, either by bouncing off superhot electrons in a see-through layer of gas called the corona that surrounds the disk, or possibly by scattering from the base of a jet of particles shooting out from the black hole. The X-rays coming from Cygnus X-1 also show a strange rhythm called quasi-periodic oscillations, or QPOs. These flickers seem to depend on how massive the black hole is. The heavier it is, the closer to the center the flickering starts. This gives scientists another way to double-check the black hole's mass. What's more, Cygnus X-1 doesn't behave like neutron stars do. Neutron stars usually pulse with regular beats or sometimes produce short, explosive bursts of X-rays. But Cygnus X-1 doesn't do either of those things. It also switches between two different X-ray states, a hard state and a soft state. In the hard state, most of the X-rays are very energetic. In the soft state, they are less energetic but more unpredictable. The hard state comes from the hot corona, while the soft state happens when the disk moves closer to the black hole and the corona disappears or cools down. When the corona reforms, the system flips back to the hard state. One explanation for these changes comes from a model called the two-component advective flow. In this idea, the hard X-rays are created by scattering seed photons from the disk, and other high-energy photons produced by fast-moving electrons in a region called the Cien bowl, centrifugal pressure-supported boundary layer. The amount of X-ray light also changes in a regular cycle every 5.6 days, especially when the black hole is behind its companion star as seen from Earth. This suggests that the X-rays are partly blocked by gas from HDE 26868's powerful wind. There's also a longer 300-day cycle, which might be caused by the slow wobbling, or precession, of the accretion disk. As matter falls toward the black hole, it loses energy. Some of that energy escapes in two narrow jets shooting out from the black hole's poles. These jets move at speeds close to the speed of light and carry away extra energy and spin. Magnetic fields in the gas may help shape and launch these jets. Interestingly, these jets don't give off much visible light or radiation, so they're considered dark. One of the jets appears to be slamming into a dense cloud in space, creating a glowing ring of energy that can be seen in radio waves and visible light. The power needed to create this nebula is estimated to be between 4 and 14 times 10 to the power of 36 ergs per second, or roughly 9 times 10 to the power of 29 watts. That's over 1,000 times more powerful than all the energy the Sun gives off. Because the opposite jet is travelling into a less dense part of space, no ring is seen on that side. In the year 2006, Cygnus X-1 made history again. It became the first stellar mass black hole known to emit gamma rays at extremely high energies, above 100 giga-electron volts. These powerful rays were detected at the same time as a burst of high-energy X-rays, suggesting both events may have come from the same process. The X-rays may have come from near the base of the jet, while the gamma rays were likely formed when the jet hit the fierce wind from HDE 26868. Now, about that companion star, HDE 226868. It's a blue supergiant and belongs to a class of stars called O9.7 IAB, which sits on the edge between two major stellar categories, Class O and Class B. This star has a sizzling surface temperature of about 31,000 degrees Kelvin and a mass estimated to be between 20 and 40 times that of the Sun. If it really is about 2,000 parsecs away, that's over 6,500 light-years, it may have a radius about 15 to 17 times larger than our Sun, and shine with 300,000 to 400,000 times more brightness. The black hole orbits HDE 26868 at a distance of around 40 times the Sun's radius, twice the size of the supergiant star itself. The gravity from the black hole stretches the surface of HDE 26868 into a teardrop shape, which also rotates, causing the star's brightness to change slightly, by about 0.06 magnitudes every 5.6 days as the stars orbit each other. This light variation is caused by the way different parts of the star's surface appear brighter or dimmer due to gravity and angle. Compared to another bright star called Alnilam, HDE 26868 shows more helium and less carbon in its outer layers. Its ultraviolet light and hydrogen alpha lines look similar to those seen from P Cygni, which means the star is surrounded by a cloud of gas that's being blown away at speeds of about 1,500 kilometers per second. Like other massive stars, HDE 26868 is constantly losing mass through a powerful stellar wind at a rate of about 2.5 millionths of a solar mass per year. That's equal to losing one whole solar mass every 400,000 years. The nearby black hole's gravity is reshaping this wind, making it flow in a more focused stream instead of spreading out evenly in all directions. The X-rays coming from the black hole's surroundings heat and ionize this wind. As the black hole moves through the wind in its 5.6-day orbit, the ultraviolet light, radio signals, and X-rays it gives off all change. The star has a gravitational boundary called the Roche lobe. Material that stays inside this zone remains part of the star, but if it crosses the line, it might fall toward the black hole. In this case, the Roche lobe seems very close to the star's surface, but not quite overflowing, so the black hole isn't ripping material directly from the star. However, a good amount of the stellar wind does pass beyond the lobe and gets pulled into the accretion disk. However, all the gas and dust floating between Earth and HDE 22 6868 dims the star's light and makes it look redder than it really is. This effect is known as interstellar extinction, and for this star it's about 3.3 magnitudes. Without this dusty veil, HDE 226, 868 would be a 5th magnitude star, just bright enough to be seen with the naked eye. The black hole known as Cygnus 1019 is one of the strangest and smallest supermassive black holes ever found in the early universe. Even though it's about 9 million times heavier than our Sun, that's actually quite small when compared to other supermassive black holes. Some of them can reach up to billions of times the mass of the Sun. Now here's where things get really puzzling. Scientists believe it takes a very long time, much longer than 600 million years, for a black hole to grow so huge. Normally black holes grow by pulling in gas, dust, stars, or even by merging with other black holes. But Cygnus 1019 seems to have grown very big, very fast. Faster than current theories can explain. To give you a comparison, the black hole at the centre of our own Milky Way galaxy weighs about 4.5 million suns, and that one is found in a much later period of the universe's history. So how did something even bigger exist when the universe was still so young? For many years, astronomers thought that supermassive black holes might have formed in the early universe, but they had no real proof. That changed with the arrival of the James Webb Space Telescope, often called JWST. Thanks to its powerful infrared vision, JWST was finally able to spot Cygnus 1019. And not only did it see it, it saw it feeding. Yes, this black hole is actively devouring matter around it. It pulls in huge swirls of gas and dust, which spin around it in a giant disk called an accretion disk. The black hole's gravity heats up this material so much that it glows brightly, almost like a cosmic diamond. But that's not all. While the black hole is munching away, powerful magnetic fields form and guide some of the gas and energy toward its poles. From there, the material is shot out in 2 enormous jets that travel at speeds close to the speed of light. These jets shine brightly and can be seen from incredibly far away. Astronomers spotted the galaxy holding this strange black hole during a special observation project called the Cosmic Evolution Early Release Science Survey, or CEERS for short. They were seeing this galaxy as it looked when the universe was only about 570 million years old. Remember, the universe today is roughly 13.8 billion years old. But Cygnus 1019 wasn't alone. Scientists also found 2 more black holes from around 1 billion and 1.1 billion years after the Big Bang, as well as 11 ancient galaxies that formed between 470 million and 675 million years after the universe began. What's so amazing about all of this is that, until recently, most of our knowledge about the early universe was just based on theory. Educated guesses, really. But now, with the help of the James Webb Space Telescope, scientists can actually see these faraway black holes and galaxies. Not only that, they can measure them too. And this isn't the only exciting discovery involving black holes. In another study, scientists noticed something strange. 2 stars were slowly changing their orbits around nearby black holes. They were moving just a tiny bit slower every year, by about 1 millisecond per year. This may not seem like much, but it could be huge news. Why? Because researchers believe the slowdown might be caused by dark matter, a mysterious type of matter that doesn't shine, reflect, or absorb light. In fact, we can't see it at all, but we know it must be there because of how it affects the things we can see. Let's break it down. Everything we can see in the universe, stars, planets, people, and galaxies, makes up only about 5% of the total universe. That's right, just 5%. The rest is made up of dark energy, around 68%, and dark matter, about 27%. Dark energy is thought to be the strange force that's pushing the universe to expand faster and faster. Dark matter, on the other hand, is what seems to hold galaxies together. Scientists believe it must exist because they see its gravitational effects on stars and galaxies, but they still don't know exactly what it is. What dark matter isn't is just as important. It's not ordinary stars or planets. It's not clouds of gas, because we'd be able to detect those. It's not antimatter, since we don't see the special gamma rays that antimatter produces when it touches normal matter. And it's probably not giant black holes either. So, what is it? No one knows for sure. Some theories suggest it might be made of exotic particles we haven't discovered yet. Others think it might be faint objects that barely give off any light. But whatever it is, it's still one of the biggest cosmic mysteries. Now, back to those two stars slowing down. Scientists ran computer simulations of the black hole systems and used a theory called the dark matter dynamic friction model. This theory says that when regular matter, like stars, moves through dark matter, it can lose speed because of the gravitational drag from the dark matter. And guess what? The simulations matched what the scientists saw in real life. This gives support to the idea that black holes might actually consume dark matter that gets too close. And as they do, dark matter might form denser regions around black holes, which could then influence how nearby stars move. If these findings are confirmed, it could be a huge step forward in understanding dark matter, one of the most mysterious parts of our universe. We've been talking a lot about black holes lately, but here's something even strange to think about. There's a fascinating theory that a very special kind of black hole, called a primordial black hole, might actually be the key to solving one of the greatest mysteries in the universe: dark matter. Now, primordial black holes are completely theoretical. That means scientists have never actually seen one or found solid evidence they exist. But if they do, they are believed to be unbelievably ancient and very, very small, at least by black hole standards. Astronomers think these black holes could have formed just a few milliseconds after the Big Bang, which happened around 13.8 billion years ago. At that time, the universe was just a newborn. There were no stars, no galaxies, not even atoms like we know them today. Everything was just a hot, dense soup of energy and particles. If primordial black holes really came into existence back then, that means they've been around for the entire history of the universe. They've seen it all, from the first stars lighting up the cosmos to the birth of galaxies, and even the rise of life on planets like Earth. The smallest of these early black holes have most likely vanished by now, slowly evaporating over time through a process called Hawking radiation. But the larger ones, the ones that started with more mass, might still be drifting silently through space, hidden in the darkness. So how did they form in the first place? Scientists think the early universe wasn't completely smooth. Some places were hotter, some cooler, and some spots were extremely dense. In those dense patches, gravity could have become strong enough to crush matter into tiny black holes. These became the primordial black holes. What's even more amazing is this. Because they formed so early, they stayed small. The rule seems to be, the earlier a black hole forms, the smaller it is. A black hole that formed just a tiny bit later might have been 1,000 times heavier than our Sun, while a primordial one could be as tiny as a pea or even smaller. The difference in mass is mind-blowing. For a long time, most scientists didn't take this idea too seriously. The theory that primordial black holes could actually be dark matter was pushed aside for decades. Dark matter, after all, is the invisible substance that makes up most of the matter in the universe, and no one has been able to find a single dark matter particle, even after many decades of searching. But something has changed. In recent years, astronomers have started to realize that there might be far more black holes in the universe than they ever imagined. This shocking discovery has led some scientists to take a second look at primordial black holes. Maybe, just maybe, these ancient hidden objects aren't just out there in the shadows, but are actually dark matter itself. Now, that's a theory worth watching. A rotating black hole is a special kind of black hole that spins around one of its own axes, just like how a spinning top twirls around its center. This spinning motion means it has something called angular momentum, which is a measure of how fast and in what way an object rotates. Interestingly, almost everything in the universe that we know of spins. Planets like Earth, stars like our Sun, entire galaxies, and even black holes all rotate. So it makes perfect sense that most black holes, which are born from collapsing stars or massive cosmic collisions, would also end up spinning. Scientists studying gravity through Einstein's theory of general relativity have found 4 exact mathematical solutions to describe different kinds of black holes. 2 of these solutions describe spinning black holes. These are called the Kerr black hole and the Kerr-Newman black hole. According to a famous idea called the no-hair theorem, once a black hole settles down and becomes stable, it can be described by just a few simple features: its mass, its spin, and its electric charge. These features can be detected from far away by studying the black hole's gravitational pull and any electromagnetic fields it creates. Everything else, like the details of how the black hole formed or what it once looked like, is either lost forever inside it or escapes to infinity. That's because nothing happening inside the black hole's event horizon, the invisible boundary around it, can influence anything outside. Now here's something interesting. When stars collapse to form black holes, they are usually spinning. This means that most black holes formed in nature should be spinning too. However, stars and other objects don't usually have a strong electric charge, so any charge a black hole has would quickly be cancelled out by attracting opposite charges. That's why most real black holes are expected to be electrically neutral, but still spinning. Because of this, when scientists talk about real-life black holes in space, they usually mean Kerr black holes, spinning but with little or no charge. Rotating black holes can form in several ways. The most common is when a massive spinning star collapses under its own gravity. Another way is when many compact objects, like stars, gas, or stellar remnants, collide or collapse together, and the whole system has some spin. In fact, because all stars spin and collisions rarely happen, without some spinning motion, it's believed that all black holes in the universe are rotating black holes. In late 2006, astronomers published some exciting data in the Astrophysical Journal. They estimated the spin rate of a black hole named GRS 1915 plus 105, located in our own Milky Way galaxy. They found that it might be spinning as fast as 1,150 times every second. That is astonishingly close to the fastest spin a black hole can possibly reach. Scientists also believe that when a rotating star collapses into a black hole, it can give off an incredibly powerful burst of gamma rays, known as a gamma ray burst. These bursts can travel across the universe and be detected by special telescopes here on Earth. Now here's the really amazing part. Rotating black holes can actually give off energy. They can do this by converting some of their spinning energy into other forms of energy. One way this happens is through something called the Penrose process, which takes place in a strange zone around the black hole called the ergosphere. This is the area just outside the event horizon where space itself is being twisted around by the black hole's spin. Over time, if energy keeps being taken from the black hole in this way, it could slowly stop spinning and become a Schwarzschild black hole, a black hole that isn't spinning at all. However, in practice, it's believed that the spin of a black hole never drops all the way to zero. The rotating black hole solutions, like the Kerr and Kerr-Newman metrics, are based on Einstein's famous field equations of 1915. These solutions are thought to be excellent models for understanding how rotating black holes behave, especially in the space outside the event horizon. Near a black hole, the fabric of space itself is so warped that light rays can bend in incredible ways. Sometimes light can even go around the black hole several times before escaping. Because of this, if you're looking at a distant galaxy that's behind a black hole, you might see several distorted images of that galaxy instead of just one. In 2021, scientists published a full mathematical explanation of how light bends around the spinning equator of a Kerr black hole. Then, in 2022, it was proven through mathematics that the solution discovered by Roy Kerr back in 1963, which describes a spinning black hole, is stable. This means black holes, as predicted by Einstein's equations from over 100 years ago, can truly exist in a stable and lasting form. However, rotating black holes can behave in 2 thermal states, heating and cooling. When they give off energy, they are losing some of their rotational energy and heating up. When they stop giving off energy, they begin to cool down. These temperature states add yet another fascinating layer to these already mysterious cosmic giants. A stellar black hole, also called a stellar mass black hole, is born in one of the most dramatic ways imaginable. It forms when a massive star, much larger than our Sun, runs out of fuel and can no longer hold itself up against the force of its own gravity. At this moment, the core of the star collapses inward, crushed under its own enormous weight. This intense collapse is known as a gravitational collapse, and it creates one of the strangest and most powerful objects in the universe, a black hole. These kinds of black holes are not giants like the ones found in the centers of galaxies. Instead, they usually have masses between 5 and a few dozen times the mass of the Sun. But don't let that fool you. These small black holes still pack an unimaginable punch. Stellar black holes are the leftovers of giant stars that explode in a spectacular way, an event known as a supernova. During this explosion, the outer layers of the star are blasted out into space, while the core collapses inward. Sometimes these explosions are so powerful that they release bursts of gamma rays, which are the most energetic kind of light in the universe. Because they come from the collapse of a massive star, stellar black holes are also called collapsers, short for collapsed stars. Even though black holes are formed in violent ways, physicists say they are surprisingly simple objects. According to an idea known as the no-hair theorem, a black hole can be fully described using just 3 things: its mass, how much matter it contains, its electric charge, if it has one, and its angular momentum, how fast it's spinning. If the star that collapsed was spinning, as most stars do, then the resulting black hole will spin too, inheriting the rotation from its parent star. The process of creating a black hole is a natural part of the life cycle of massive stars. As a star burns its nuclear fuel, it creates energy that pushes outward and keeps gravity in balance. But once the fuel runs out, the star can no longer support itself. Gravity takes over, pulling everything inward. Depending on how much mass is left behind after the star dies, the core might become a white dwarf or a neutron star. Both are incredibly dense, compact remnants. In some rare and still theoretical cases, the core might even become a quark star, made of tiny building blocks called quarks. But if the leftover core is too heavy, it passes a point of no return called the Tolman-Oppenheimer-Volkoff limit, often shortened to the TOV limit. If the collapsing core is more massive than this limit, nothing in the universe can stop it from shrinking. The star continues to collapse until it becomes a black hole, a place in space where gravity is so strong that not even light can escape. Back in the year 1939, scientists estimated the TOV limit to be about 0.7 times the mass of our Sun. However, newer research, including a study from 1996, suggests the limit is more likely somewhere between 1.5 and 3 times the mass of the Sun. One of the heaviest neutron stars ever discovered is called PSR J 0740 + 6620. It was found in September of the year 2019, and it weighs about 2.14 times the mass of the Sun. According to Albert Einstein's theory of general relativity, a black hole can, in theory, be any mass, from tiny to huge. But creating a very small black hole would require the matter to be compressed to extreme densities. In reality, no known star can collapse to form a black hole smaller than a few times the mass of the Sun. If black holes smaller than this do exist, they probably weren't formed by stars. Instead, scientists think they might have formed during the very early moments after the Big Bang, and they are called primordial black holes. Until the year 2016, the biggest stellar black hole known had a mass of around 15 2/3 times that of the Sun. But in September of the year 2015, something incredible happened. Scientists detected gravitational waves, ripples in the very fabric of space and time, from 2 smaller black holes crashing into each other. When they merged, they formed a spinning black hole with a mass of about 62 times the mass of the Sun. This was one of the first direct pieces of evidence that black holes really exist, and that they can grow larger by merging. In June of the year 2020, scientists announced the discovery of the smallest stellar black hole ever found, at least at that time. It's part of a binary system called 2MassJ 05 215658 plus 4 359220. This tiny black hole weighs just 3.3 times the mass of the Sun, and its diameter, only about 19.5 kilometers across. That's smaller than many cities on planet Earth. Besides stellar black holes, astronomers have also found signs of two other major types: intermediate mass black holes, which may be found in the centers of globular clusters. These are tightly packed groups of stars. Supermassive black holes, which sit in the heart of almost every galaxy, including our own Milky Way. These cosmic monsters can be millions or even billions of times more massive than the Sun. Sometimes, a stellar black hole shares a cosmic dance with a normal star in what's called a binary system. When they orbit each other closely, the black hole can begin to pull matter off its companion star. As this gas and dust spiral toward the black hole, they form a hot disk around it and get incredibly hot, reaching temperatures of hundreds of millions of degrees. At those temperatures, the matter glows brightly in the form of X-rays, which scientists can detect with special telescopes. Even though the black hole itself is invisible, these X-rays help astronomers see it. Meanwhile, the regular star that's losing material can be seen with ordinary telescopes. Neutron stars and black holes can sometimes act in similar ways, especially when it comes to the energy they release. To tell them apart, scientists carefully measure their mass. So far, all confirmed neutron stars weigh less than 3 times the mass of the Sun. If a mysterious, compact object is heavier than that and doesn't behave like a neutron star, then scientists are fairly sure it must be a black hole. Sometimes, astronomers discover pairs of stars or space objects, known as binary systems, in places where they really shouldn't be, far above or below the flat plane of our Milky Way galaxy. This strange positioning is believed to be caused by something called natal kicks. These kicks are powerful jolts that happen when a black hole is born from the collapse of a dying star. The kick gives the newborn black hole a push, flinging it out of its original place. What's fascinating is that these black hole kicks seem to behave very much like the kicks given to neutron stars, even though black holes are much heavier. You might expect that because black holes have more mass, they wouldn't move as fast after a kick. But in reality, they often do. One explanation for this surprising behavior is that when a star collapses into a black hole, it doesn't eject all its outer layers evenly. Some of the material falls back onto the black hole, giving it an extra push, like a cosmic afterburner that increases its speed. Scientists also believe that not all black holes can be formed in the same way. Some models of how stars evolve suggest that black holes within certain mass ranges simply can't form directly from a star collapsing. These are called mass gaps, one at the lower end and one at the upper end of the black hole mass scale. The lower mass gap is the mysterious space between 2 and 5 times the mass of our Sun, where black holes seem to be missing. There are very few black holes observed in this range, even though it's just above the heaviest neutron stars. Some scientists believe this gap might be real, but others think that we just haven't found enough black holes yet in this range. There's also a theory that black holes in this mass range might not come from single stars collapsing, but instead from 2 neutron stars merging together. This is where the LIGO and Virgo observatories come in. These facilities detect gravitational waves, ripples in space caused by massive collisions. So far, they've found 3 events that may involve black holes within this lower mass gap. Another piece of evidence comes from a strange star system, where a bright, fast-spinning star appears to be orbiting an invisible companion. This companion doesn't give off light, not even X-rays, but seems to have a mass of about 3.3 times the mass of our Sun. This suggests it might be a quiet, low-mass black hole that isn't pulling in material right now, which is why we don't see it. There could be many more of these invisible black holes out there that are flying under our radar. Now let's talk about the upper mass gap, another curious missing range of black hole masses. This gap is thought to lie between around 50 to 150 times the mass of the Sun. Some estimates put it between 52 and 133 solar masses. This gap is connected to a dramatic and powerful kind of explosion called a pair instability supernova. In this event, a supermassive star gets so hot and energetic that gamma rays collide with atomic particles inside it, breaking the delicate balance of pressure. As a result, the core collapses and causes a massive explosion that completely tears the star apart, leaving no black hole behind. These rare explosions can only happen in stars with masses between about 130 and 250 times the mass of the Sun, and mostly in stars made almost entirely of hydrogen and helium. These were the kinds of stars that existed billions of years ago, known as the population 3 stars, thought to be the first stars in the universe. Some newer theories suggest that the upper mass gap might begin at a lower point, maybe even 45 solar masses, because of a process called pair instability pulsational mass loss. This happens before the supernova, when the star loses large amounts of mass in giant pulses, and for stars that don't spin, the lower edge of this mass gap might be as high as 60 solar masses. There's also speculation that extremely massive stellar cores, those weighing more than 133 solar masses, might collapse directly into black holes without any explosion at all. If that's true, we wouldn't expect to see the glowing remains of a supernova, making it even harder to detect such events. This idea suggests that the start of the upper mass gap may mark the boundary where regular black hole formation stops. A few years ago, astronomers studying a system known as LB1 thought they had found a black hole with a mass of about 70 times the mass of the Sun. If true, this black hole would fall right into the middle of the upper mass gap. But after more detailed analysis, scientists began to doubt that original discovery. It might not have been a black hole after all. Even if black holes can't be born directly into these mass gaps, they might still end up there by merging. For example, if two smaller black holes crash into each other, the new black hole they form could fall right into the gap. Closer to home, our own Milky Way galaxy is filled with candidates for stellar mass black holes. These are black holes that formed from massive stars, not to be confused with the supermassive black hole that sits at the very center of our galaxy. Many of these stellar mass black holes are found in X-ray binary systems, where a black hole is stealing material from its companion star. As this material swirls into the black hole, it forms a glowing accretion disk that gives off powerful X-rays, making the system easier to detect. The black holes in these systems are estimated to have masses ranging from about 3 to more than 12 times the mass of the Sun. Long before the first stars were born, when the universe was still just a newborn, only fractions of a second old, some scientists believe a very strange kind of black hole might have formed. These are called primordial black holes, or PBHs for short. They are unlike the black holes we see today, and they might hold secrets about the universe that no one has yet unlocked. Today, we know that most black holes are created when massive stars die. A giant star explodes in a supernova, and its heavy core collapses under the force of gravity, forming a black hole. But primordial black holes are thought to have formed in a completely different way. In the earliest moments after the Big Bang, the universe was incredibly hot, filled with radiation and tiny particles moving at nearly the speed of light. It was during this period, known as the inflationary era, that tiny but extremely dense clumps of matter might have been crushed by their own gravity. These clumps didn't come from stars at all. Instead, they may have collapsed straight into black holes, forming just milliseconds after the universe began. That means these black holes could have existed long before stars, galaxies, or even atoms as we know them. Since primordial black holes didn't come from stars, they don't follow the same rules as regular black holes. Most black holes we know today are a few times heavier than our Sun. But PBHs could be any size. Some might be smaller than an atom, while others could be thousands of times heavier than the Sun. Their sizes could vary wildly. The idea of primordial black holes was first introduced in the year 1966 by two Soviet physicists, Yakov Zeldovich and Igor Novikov. Then, in the year 1971, a young physicist named Stephen Hawking took this idea further. He began exploring what would happen if black holes really could form in the early universe. Even today, more than 50 years later, primordial black holes are still just a theory. Scientists haven't found direct proof that they exist, but they have many reasons to believe they might. In September of the year 2022, a team of scientists proposed that PBHs might help explain a strange discovery made by the James Webb Space Telescope. The telescope had found huge galaxies forming very early in the universe, far earlier than anyone thought possible. PBHs might have helped these galaxies grow so fast by acting as seeds that pulled in matter and jump-started their formation. PBHs have also been suggested as a possible answer to one of the biggest mysteries in science. dark matter. Dark matter is a strange, invisible form of matter that doesn't give off light and can't be seen with any telescope. Yet, it seems to make up most of the matter in the entire universe. Some researchers think that primordial black holes could actually be dark matter. According to this idea, if PBHs are common enough, they might account for nearly all the dark matter in the universe. This idea has gained support in recent years, especially thanks to the LIGO and Virgo detectors, which can hear gravitational waves, ripples in space caused when black holes collide. The James Webb Space Telescope has also provided clues that seem to support the PBH theory. At first, scientists thought that if PBHs existed, they would all be about the same size. This idea is called a monochromatic mass distribution. But the results from LIGO and Virgo changed that view. They showed that black holes come in many different sizes, not just one. Some of the newest data from the James Webb Telescope also supports the idea that PBHs could have a wide range of sizes, many of them weighing about the same as our Sun. Some PBHs might be incredibly small, as tiny as an asteroid, but with the mass squeezed into something the size of a hydrogen atom. These tiny black holes could be flying through space at fantastic speeds. In fact, it's possible that one might even be somewhere inside our own solar system right now. Most of the time, if such a small black hole passed through a star, it would go right through, like a bullet flying through fog. But if it were moving slowly enough, it might get pulled in by the star's gravity. Stephen Hawking even once suggested that our Sun might be hiding one of these tiny black holes inside it. Depending on the theory, a primordial black hole might have started with a mass as small as 10 to the -8 kilograms, something scientists call a Planck relic, or it might have been thousands of times heavier than the Sun. However, PBHs that were born with a mass smaller than 100 billion kilograms probably don't exist anymore. They would have slowly vanished over time due to a strange effect called Hawking radiation, where tiny black holes slowly evaporate. So only the bigger PBHs would still be around today. Primordial black holes are also different from ordinary matter, like the kind that makes up stars, planets, people, and trees. They might be made of non-baryonic matter, which means they don't follow the same rules as regular atoms. This is another reason why some scientists believe PBHs might be connected to dark matter. Some researchers even think these early black holes could have helped create the supermassive black holes that sit at the centers of huge galaxies, or the intermediate-sized black holes found in smaller galaxies. In this way, primordial black holes might be the original seeds from which some of the biggest black holes in the universe grew. PBHs are also part of a broader class of mysterious objects called MACHOs, which stands for Massive Compact Halo Objects. These are objects that are good candidates for dark matter because they are massive, don't shine, and don't bump into other things very often. MACHOs move slowly through space, and might have formed within the first second after the Big Bang. However, not all scientists agree with these ideas. Some space observations suggest there can't be too many PBHs, or we would have noticed them already. These scientists believe PBHs probably make up only a small part of the dark matter in the universe. Still, others suggest PBHs could play an important role, especially if they tend to group together in small clusters. In fact, there might be a PBH weighing about 30 times more than the Sun sitting at the center of each cluster. In March of the year 2016, just 1 month after scientists announced that they had detected gravitational waves for the very first time using the upgraded Advanced LIGO and Virgo detectors, 3 different research groups came forward with an exciting idea. Maybe those waves had come from 2 primordial black holes merging together. Each of these black holes had about 30 times the mass of our Sun, which was very surprising. 2 of the groups said this was exactly what we would expect if PBHs made up all the dark matter, but only if they were hiding in small galactic halos, like faint dwarf galaxies or globular clusters. The 3rd group disagreed. They said the number of mergers seen by LIGO was too low, and that PBHs could only make up less than 1% of the dark matter in the universe. The unexpectedly large black holes discovered by LIGO brought new attention to the idea of PBHs, with masses between 1 and 100 times the mass of the Sun. Scientists are still trying to figure out whether this theory matches other observations, like the lack of microlensing events, patterns in the cosmic microwave background, the size of tiny galaxies, and the missing X-ray and radio signals near the centre of our galaxy. In the month of May, in the year 2016, a scientist named Alexander Kashlinsky shared a truly fascinating idea with the world. While carefully studying the universe's background radiation, the faint afterglow of ancient cosmic events, he noticed something strange. In particular, he found unusual patterns in gamma rays and X-rays coming from regions of the sky where no visible sources like stars or galaxies could be seen. It was as if something invisible was shining through the darkness. These strange signals puzzled scientists for years. Kashlinsky proposed a bold explanation. He believed that these mysterious rays might actually come from primordial black holes, incredibly ancient black holes that may have formed just tiny fractions of a second after the Big Bang, long before the first stars were born. He even suggested that if these black holes were all about the same size and were as common as dark matter, they might be the source of this unexplained radiation. It was a thrilling possibility, one that could link black holes to one of the greatest mysteries in all of science. Then, in the month of August in the year 2019, another scientific study offered an even more astonishing idea. This new research suggested that all the dark matter in the universe, the invisible stuff that makes up most of the mass in the cosmos, might actually be made entirely of primordial black holes, and not giant ones either. These would be black holes about the size of asteroids, small but incredibly heavy. Imagine countless tiny but dense black holes scattered throughout space, quietly making up most of the universe's unseen mass. It was a daring theory that sparked a wave of curiosity. Only 1 month later, in the month of September in the same year, 2019, two scientists named James Unwin and Jakob Schultz came up with yet another surprising idea. They thought there might be a black hole hiding inside our own solar system. According to them, this black hole could have a mass between 5 and 15 times the mass of the Earth. But it wouldn't be a giant monster. Amazingly, it might be no bigger than a tennis ball. This incredibly compact object could be sitting far beyond the planet Neptune, in a distant region called the Kuiper Belt. Their theory was based on something odd. A few distant space objects were moving in strange, unexpected ways. It looked like something massive but invisible was pulling on them. For years, scientists had been hunting for a mysterious Planet 9 that might be causing this. But Unwin and Schultz had a radical new idea. Maybe Planet 9 wasn't a planet at all. Maybe it was a primordial black hole. In the next month, October of the year 2019, scientists Derek Inman and Yassine Ali Haimoud explored how the large-scale structure of the universe might affect our understanding of something called the cosmic microwave background, CMB. The CMB is the faint radiation left over from the Big Bang, like an ancient echo frozen in time. Their research showed that the small shifts in matter that happened as galaxies formed were not strong enough to change what we know from the CMB. That meant scientists could still rely on the CMB data when studying black holes in the early universe. It was still a solid foundation for discovery. Jump ahead to the month of September in the year 2021. A team of scientists from the Nanograv collaboration made a thrilling announcement. They had picked up a low-frequency signal that could be linked to gravitational waves, tiny ripples in the fabric of space and time itself. Some researchers believed that this gentle hum across the universe might come from groups of primordial black holes. If true, this would give us a brand new way to detect these ancient cosmic ghosts, even though they're normally invisible. Then, in the month of September in the following year, 2022, scientists once again turned their focus to primordial black holes. This time, they were trying to solve a new puzzle. The powerful James Webb Space Telescope, one of the most advanced space telescopes ever built, had spotted huge galaxies forming far too early in the universe's history, just a few 100 million years after the Big Bang. According to existing theories, galaxies that big shouldn't have formed so soon. But if primordial black holes had helped galaxies grow faster and earlier than expected, then these early giants suddenly made a lot more sense. A few months later, on the 26th day of November in the year 2023, scientists made a discovery that stunned the astronomy world. For the first time ever, they found strong evidence of something called an overmassive black hole galaxy, or OBG. This kind of galaxy may have formed in a very rare way, through a process called direct collapse. Instead of being born from the death of a star, this black hole formed straight from a massive cloud of gas, skipping the usual steps. The galaxy where this happened was a faraway one called UHZ1, and at its heart was a blindingly bright quasar, a powerful object powered by a supermassive black hole. Scientists used both the Chandra X-ray Observatory and the James Webb Space Telescope to study it. The discovery opened a new chapter in understanding how black holes and even galaxies might form. In the year 2024, a group of researchers led by physicist Bernard Carr took a fresh look at how primordial black holes might have first appeared. Their review focused on a tiny moment in time called the quantum chromodynamics epoch, which happened less than 100,000th of a second after the Big Bang. According to their findings, the black holes formed during this moment would follow a unique pattern in their sizes today, with certain bumps or peaks in mass. One of these bumps was near one solar mass, which means about the same mass as our Sun. But how could such ancient black holes have formed in the first place? Scientists believe that primordial black holes might have appeared within the very first second after the Big Bang. They could have emerged during the inflationary era, a period when the universe expanded incredibly fast, or early in the radiation-dominated era, when light and energy filled the cosmos. For a black hole to form, you need a very dense region of matter, where gravity becomes so strong that everything collapses inward. These dense pockets might have been caused by tiny differences in how matter was spread out in the young universe, known as density fluctuations. There are a few ways these fluctuations might have formed. One idea involves something called axion inflation. In this theory, a mysterious particle called an axion acts like a strange kind of field during inflation, creating ripples and waves in space. These waves could have become the seeds for black holes. Another possibility is reheating, a brief moment that came right after inflation ended. During this time, the inflaton field, the energy field believed to have driven inflation, broke down into ordinary particles. As these particles tried to settle into a balanced state, the process may have been messy, leaving behind clumps of matter that were heavy enough to collapse into black holes. A third explanation comes from cosmic phase transitions. These were times when the universe changed its state, similar to how water turns into ice. Such shifts could have produced dense regions or released powerful particles, both of which might have collapsed under their own gravity and become black holes. Now let's go back to one of the biggest and strangest mysteries in modern science, the mystery of dark matter. This puzzle was first suggested all the way back in the year 1933 by a Swiss-American astronomer named Fritz Zwicky. He noticed something odd when he studied groups of galaxies. They were moving as if there was a lot more matter pulling on them than what we could actually see. Scientists later realized that this wasn't just happening in a few galaxies, it was happening everywhere. It was as if some kind of invisible material was out there, adding extra gravity to the universe. This mysterious stuff became known as dark matter. Even though no one has ever seen dark matter directly, scientists are almost certain it must exist, because galaxies and galaxy clusters just don't behave the way they do without it. But what could dark matter be made of? One fascinating idea is that primordial black holes, often called PBHs, might be the answer. Primordial black holes are very different from the black holes we usually hear about. Normal black holes are formed when giant stars collapse at the end of their lives. But primordial black holes might have formed during the very first moments after the Big Bang, when the universe was still extremely hot, dense, and chaotic. These PBHs might help explain dark matter in three exciting ways. First, if there are enough of them floating around, they could actually make up all or most of the dark matter in the entire universe. Second, unlike other dark matter candidates like WIMPs, which stands for weakly interacting massive particles, PBHs can create gravitational waves, which are ripples in space-time. These waves can be detected with advanced instruments like LIGO and Virgo, giving us a way to actually listen to the presence of black holes. Third, PBHs might explain some strange cases of gravitational lensing, which is when the light from faraway stars or galaxies bends and twists due to invisible objects in its path. Sometimes this bending doesn't match what we'd expect from ordinary matter. PBHs might be the hidden culprits. Even though scientists haven't yet confirmed that PBHs are the true form of dark matter, the evidence is growing. Experts like Bernard Carr and his colleagues have been studying this idea for years, hoping that the key to dark matter lies in the very birth of the universe. What makes PBHs even more interesting is that they don't have to be tiny. They could come in a wide range of sizes, from much smaller than a grain of sand to as massive as a mountain or even bigger. Because of this, some scientists believe PBHs might have helped form the earliest galaxies, possibly even before the first stars had a chance to shine. Now let's go back to another cosmic mystery, this one introduced in the year 1974 by a brilliant Soviet physicist named Yakov Zeldovich. He came up with a puzzling idea in cosmology called the cosmological domain wall problem. He suggested that during the early universe's rapid changes, known as phase transitions, strange, invisible boundaries called domain walls might have formed. These walls would have been packed with energy, and if too many of them were created, they could have completely messed up the way the universe developed. But here's the clever part. PBHs might actually fix this problem. Here are 3 ways PBHs could help with the domain wall issue. 1. If PBHs formed very early, their strong gravity could have pulled matter toward them and caused it to clump together. This clumping might have prevented the domain walls from forming in the first place. 2. If the domain walls had already appeared, PBHs might have helped destroy them. Their gravitational pull could have caused the walls to collapse, possibly turning into more PBHs. 3. PBHs might simply fit into the universe without disrupting anything. For example, if we found PBHs with masses between 10 to the power of 12 kilograms and 10 to the power of 13 kilograms, that could be just the right amount to explain all the dark matter in the universe, without causing any problems or breaking the laws of physics as we know them. But that's not the end of Zeldovich's brilliant ideas. In the late 1970s, he also proposed something called the cosmological monopole problem. This problem has to do with magnetic monopoles, which are strange, theoretical particles that have only one magnetic pole, either north or south. All regular magnets always have both. According to some theories, monopoles should have formed in the early universe, yet no one has ever seen one. Again, PBHs might provide an answer. One idea is that if these magnetic monopoles ever existed, they may have been pulled into PBHs by their gravity and swallowed up. Another idea is that PBHs could have spread matter out in the early universe, scattering the monopoles so far apart that they're nearly impossible to detect today. Now, let's add a twist from one of the most complex and fascinating theories in physics, string theory. According to general relativity, the tiniest PBHs should have completely vanished by now, slowly evaporating over time due to something called Hawking radiation, a process first proposed by Stephen Hawking in the year 1974. But string theory suggests something wild. There might be an extra, hidden spatial dimension beyond the 3 we already know. If that's true, then gravity might behave differently on small scales. This could slow down the evaporation of tiny PBHs, allowing them to survive much longer than expected. In simple terms, this hidden dimension could add extra energy that helps keep small PBHs from disappearing. If this theory is correct, there could be thousands of miniature PBHs quietly floating around inside our own Milky Way galaxy. To test this idea, scientists have turned to a powerful space telescope called the Fermi Gamma Ray Space Telescope, which was launched by NASA on June 11, 2008. If this telescope detects specific patterns in gamma ray bursts, like tiny flickers or ripples in the energy, it could be the first real sign that PBHs and the extra dimensions predicted by string theory are real. Scientists have also tried to figure out just how many PBHs might exist and how massive they could be. One way to study this is through Hawking radiation. According to Hawking, all black holes slowly lose mass over time by releasing tiny amounts of energy. The smaller the black hole, the faster it evaporates. When it gets really small, it could end its life with a sudden, powerful explosion, similar to a massive hydrogen bomb that releases millions of megatons of energy in an instant. For comparison, a regular black hole that has a mass about 3 times that of our Sun would take about 10 to the power of 69 years to fully evaporate. That's an amount of time so huge it makes the current age of the universe, about 13.8 billion years, look like a blink of an eye. But PBHs could be far smaller. A PBH with a mass around 10 to the power of 11 kilograms would have a lifetime close to the current age of the universe. If many of these PBHs were formed during the Big Bang, We might even be able to see some of them finishing their lives and exploding right now, somewhere in our own galaxy. In the month of June in the year 2008, NASA launched a powerful space telescope called the Fermi Gamma Ray Space Telescope. One of its main missions was to search for strange and powerful events in the universe, including signals that might come from primordial black holes, tiny black holes that may have formed right after the Big Bang. Based on what Fermi has observed over the years, scientists now believe that if primordial black holes exist, they cannot make up more than 1% of all dark matter, at least not the ones that weigh up to 10 trillion kilograms, which is 10 to the power of 13 kilograms. There's another clue. If there had been a large number of these tiny black holes in the early universe, their energy would have affected how the first light elements, like hydrogen and helium, were created. The balance of these elements is very precise, and anything that disturbed it would leave a clear mark in the cosmos. But here comes a difficult twist. A famous physicist named Stephen Hawking once predicted that black holes should slowly lose mass by giving off radiation, something now called Hawking radiation. If this radiation really exists, then tiny black holes could eventually vanish. But if Hawking radiation turns out to be just a theory and not real, then these small black holes would be almost impossible to detect. They are so tiny and have so little gravity that they wouldn't pull in much matter or give off much energy, making them nearly invisible. Back in the earliest moments of the universe, just after the Big Bang, some scientists think that extremely tiny black holes might have formed out of collapsed clumps of energy and matter. These are called primordial black holes, or PBHs for short. If they did exist, they could have pulled in matter around them, heating it up and releasing energy into space. This energy would have had a big effect during a critical moment in the universe's early history, an event called recombination, when the universe cooled enough for atoms to form and light began to travel freely through space. This ancient light, known as the cosmic microwave background, or CMB, still fills the universe today. It carries tiny temperature differences called anisotropies, which scientists can measure with amazing accuracy. A space telescope called Planck, which studied the CMB in great detail, showed that if primordial black holes were as heavy as between 100 and 10,000 times the mass of our Sun, they probably couldn't make up a large part of dark matter, at least according to the simplest ideas we have. But some scientists think this might change if we use more complex models of how the universe works. There's another fascinating theory. Maybe dark matter, the invisible stuff that makes up most of the matter in the universe, is made of special particles called WIMPs, which stands for weakly interacting massive particles. If these WIMPs gathered around a primordial black hole in a kind of cloud, they could bump into each other and destroy each other in a process called annihilation. This would release powerful light in the form of gamma rays, which space telescopes like Fermi are designed to detect. Now, in the years ahead, scientists will use many advanced instruments and experiments to continue hunting for signs of these mysterious black holes. The Square Kilometre Array, SKA. This giant radio telescope will study how primordial black holes may have changed the time when the first stars and galaxies began to shine. If black holes released energy by pulling in gas, they could have changed how the universe became reionized when light returned after a period of cosmic darkness. Gravitational wave detectors, LIGO and Virgo. These detectors have already found black holes crashing into each other. If they detect black holes that are smaller than 1.4 times the Sun's mass, it would be unusual, since regular black holes from dying stars are usually bigger than that. Finding smaller ones might be a strong hint that they are primordial. These detectors can also see if the black holes are moving in strange elongated orbits, which would be another possible clue. LISA and pulsar timing arrays. LISA, short for Laser Interferometer Space Antenna, and other tools like pulsar timing arrays are being built to detect very faint ripples in space and time, caused by primordial black holes orbiting each other before they crash together. Tiny dwarf galaxies and their star clusters. Some small galaxies are filled with dark matter. If primordial black holes are hiding there, studying the stars in their centers might reveal something. If a primordial black hole is nearby, it could slightly change the motion of stars around it. By carefully observing star movements, scientists might find signs of one. Some researchers have even suggested that if a tiny black hole passed through Earth, it would make a special kind of sound-like signal. Since these black holes are small but very heavy and extremely fast, They could zip through the planet with only a few tiny interactions, without causing any damage. If a primordial black hole ever passed through a star, its powerful gravity might cause the star to ripple or shake. These tiny vibrations might be detected by astronomers. When a black hole passes in front of a distant star or a bright object like a quasar, its gravity can bend the light. Scientists can look for this strange bending of light, called microlensing, to find hidden black holes. If a tiny but fast-moving primordial black hole passed through the solar system, it might tug slightly on a planet like Mars. This tug could be seen as a small, sudden change in its orbit. Even though none of these tools were made specifically to find primordial black holes, each one can offer valuable clues. Together they form a powerful toolbox for solving the mystery. Cosmic Explorer and Einstein Telescope. These are future versions of LIGO and Virgo that will be even more sensitive. They will be able to detect gravitational waves from farther back in time, possibly spotting the faint signals left behind by primordial black holes. Nanograv. This project recently picked up a mysterious signal. If it turns out to be from gravitational waves caused by black holes smaller than the Sun, it might be the first strong evidence for primordial black holes. LISA will also be able to detect a special type of event where a small black hole spirals into a much bigger one. This could offer more ways to discover primordial black holes and confirm signals like the one Nanograv saw. Atomic Experiment for Dark Matter and Gravity Exploration in Space. This future experiment will try to catch signals from medium-sized black holes crashing into each other. If successful, it might help prove that primordial black holes were involved in forming the supermassive black holes we see today in giant galaxies. Nancy Grace Roman's Space Telescope. This space telescope will use a method called astrometric lensing, where the position of a star shifts slightly when a dark object moves in front of it. It might be able to detect black holes this way. Vera C. Rubin Observatory, LSST. This ground-based telescope will look for brief flashes of light caused by microlensing. It could measure the masses of hidden objects, and might even detect rare cosmic explosions called kilonovae, which could be linked to primordial black holes. NGVLA, Next Generation Very Large Array. This powerful radio telescope will help improve results from projects like Nanograv, and help tell whether gravitational wave signals are really coming from primordial black holes, fast radio bursts, FRBs. These sudden, powerful bursts of radio waves come from far away. If a primordial black hole passes between Earth and an FRB, it could bend the signal. By studying many FRBs, scientists might see patterns that suggest the presence of these ancient black holes. There is also a mysterious part of the gamma-ray spectrum known as the MeV band, which has not been fully explored. If scientists build new detectors to study this area, they could set tighter limits on how many primordial black holes exist with masses similar to large asteroids. For example, if a primordial black hole has a mass around 5 × 10 to the power of 19 grams, which is about the mass of a large asteroid, it would be giving off powerful TeV gamma rays as it slowly evaporates. These rays would show up as random bursts of energy all over the sky. Special wide-field telescopes, designed to catch fast, bright events, could help detect them, even if they only observe small parts of the sky at once. It's important to remember that not all black holes form in the same way. Some come from huge gas clouds collapsing long after the Big Bang. But primordial black holes are unique. They might have formed in the first tiny fraction of a second after the Big Bang itself, from collapsing waves of energy in the newborn universe. As scientists continue to build better tools and study the skies with more precision, they may finally uncover the truth about these mysterious ancient black holes and unlock the secrets they have been hiding for billions of years. Supermassive black holes are the true giants of the universe, the biggest and most powerful type of black hole we know. These enormous beasts can weigh as much as hundreds of thousands, millions, or even billions of times more than our own Sun. Just imagine trying to squeeze the mass of 1 billion suns into a space smaller than a galaxy. It's almost impossible to picture, but that's exactly what a supermassive black hole is. Black holes themselves are among the strangest and most mysterious objects in space. They form when a huge amount of matter collapses under its own weight, creating a spot in space where gravity becomes so strong that absolutely nothing, not even light, can escape. Because light can't get out, they appear completely black, like invisible traps in space. We can't actually see them directly, but scientists can tell where they are by watching how they affect nearby stars, glowing gas, and light that passes near them. Over the years, astronomers have found strong clues that nearly every large galaxy in the entire universe has a supermassive black hole sitting quietly, or sometimes not so quietly, at its centre. Our own Milky Way galaxy is no exception. Right in its middle lies a massive black hole called Sagittarius A star. It doesn't shine with its own light, but when clouds of gas and dust fall into it, they heat up and produce incredible bursts of energy that we can detect with telescopes. When gas, dust, or other space material gets pulled toward one of these black holes, it doesn't fall straight in. Instead, it starts spinning very fast and heats up to unbelievable temperatures. This creates dazzling displays of energy so bright that we call them active galactic nuclei. If these light shows become especially powerful, they are known as quasars. Some of the brightest things in the entire universe, a single quasar can outshine every star in its galaxy combined. Thanks to a special global network of powerful radio telescopes called the Event Horizon Telescope, scientists have recently done something once thought impossible. They actually captured images of two supermassive black holes. One of them is located in a giant galaxy called Messier 87, and the other is our very own Sagittarius A star in the heart of the Milky Way. For a black hole to qualify as supermassive, it needs to weigh at least 100,000 times as much as the Sun. But most of them are much heavier than that. Many tip the cosmic scales at millions or even billions of solar masses. Now here's something that might surprise you. Despite their mind-blowing weight, supermassive black holes aren't as dense as you might expect. In fact, if you could spread their mass out evenly across the volume inside their event horizon, the invisible boundary that marks the point of no return, their average density might actually be less than that of water. This is because as a black hole gets more massive, its size increases even faster, spreading the mass over a much larger space. Here's a fun and mind-bending comparison. Imagine a black hole that doesn't spin and has no electric charge. If it had the same mass as 1 billion suns, its event horizon, the boundary around it, would be almost as wide as the orbit of Uranus, the seventh planet from the Sun. That's about 19 times farther than the distance from Earth to the Sun. And then there are the real monsters, ultramassive black holes. These cosmic titans are even larger than supermassive ones and can weigh more than 5 billion times the mass of the Sun. Some of the biggest known examples are believed to be hiding at the centres of galaxies like TON 618, NGC 1666, ESO 444-46, and NGC 4889. Most scientists believe that there's a natural limit to how big black holes can grow, probably around 50 billion times the Sun's mass. But in the year 2020, a new study challenged that idea and suggested that even more enormous black holes could exist. These theoretical monsters were given the name stupendously large black holes, or slabs for short. According to the study, slabs could weigh more than 100 billion suns. One possible candidate might be at the centre of a galaxy cluster called Phoenix A. Now, the story of how scientists first stumbled upon these incredible objects is just as fascinating as the black holes themselves. Back in the year 1963, a Dutch-American astronomer named Martin Schmidt was studying a mysterious object known as 3C 273. At first, people thought it was a strange kind of star, but when Schmidt looked carefully at the light it was giving off, he noticed something odd. It showed signs of redshift, meaning it was moving away from Earth at a very high speed. According to Hubble's law, this meant the object had to be extremely far away, billions of light years from Earth, but it was still glowing as brightly as hundreds of entire galaxies. Scientists gave these kinds of objects a new name, quasars. By the year 1964, researchers had discovered 4 quasars. These mysterious objects were incredibly small in size, no more than about 3 light-years across, but were giving off enormous amounts of energy. Something incredibly powerful had to be behind it. In the early 1960s, 2 scientists named Fred Hoyle and W. A. Fowler came up with a new idea. They suggested that maybe quasars were powered by huge, supermassive stars burning hydrogen at their cores. These stars, they imagined, could weigh anywhere from 100,000 to 1 billion times as much as the Sun. However, this idea had a big problem. The famous physicist Richard Feynman pointed out that stars beyond a certain size would become unstable and collapse under their own gravity, turning into black holes unless something prevented that collapse. Later, Fowler proposed that maybe these stars went through a cycle of collapsing and exploding, which could explain the bursts of energy seen in quasars. In the year 1972, two scientists named Appenzeller and Fricker used computer models to test this idea. They discovered that even if a supermassive star tried to burn its fuel, it would still eventually collapse into a black hole. One of their models looked at a star with 750,000 times the mass of the Sun, and sure enough it turned into a black hole. Back in 1964, two brilliant thinkers, Edwin E. Salpeter and Yakov Zeldovich, suggested that the intense energy of quasars might come from matter falling into a giant black hole. They estimated that to produce such energy, the black hole would need to be about 100 million times more massive than our Sun. Then, in 1969, another scientist named Donald Lynden Bell expanded on this idea. He explained that gas falling toward a massive object like a black hole wouldn't just fall straight in, it would spiral around and form a flat disk, similar to how water swirls down a drain. This spinning disk would slowly get pulled in, releasing energy along the way. Lynden Bell also noticed that many nearby galaxies had faint centers, which meant they might have once been quasars that had gone quiet. Meanwhile, in the year 1967, two researchers named Martin Ryle and Malcolm Longair proposed another intriguing theory. They suggested that powerful radio waves coming from distant galaxies could be explained by particles being blasted out of the galaxies at nearly the speed of light. Later, in 1973, they teamed up with Peter Scheuer and proposed that the energy for these high-speed jets might come from the dense cores of galaxies, possibly from the immense power of supermassive black holes. In 1970, scientists Arthur M. Wolf and Geoffrey Burbidge looked closely at elliptical galaxies, those that are round or oval in shape. They noticed that stars near the centers of these galaxies were moving around much faster than expected. The only explanation was that there must be a huge amount of unseen mass at the center, much more than could be accounted for by stars alone. They concluded that it could be one gigantic black hole, as massive as 10 billion suns, or a group of many smaller black holes, each less than 1,000 times the mass of the Sun. More strong evidence came in the year 1978, when astronomers studied the elliptical galaxy called Messier 87. They found signs of a dark, massive object in the center, estimated to be 5 billion times the mass of the Sun. Soon after, similar signs were found in other galaxies too, including the Andromeda Galaxy in 1984 and the Sombrero Galaxy in 1988. Then, in 1971, Donald Lynden Bell and Martin Rees made a bold prediction. They thought the center of our own Milky Way galaxy might also contain a supermassive black hole. Just a few years later, on February 13th and 15th of 1974, astronomers Bruce Ballack and Robert Brown found something exciting. Using a special radio telescope in Green Bank, they discovered a strange radio source at the center of the Milky Way. It gave off a kind of radiation called synchrotron radiation, and it didn't seem to move. Because of its strong gravity, they realized this could be the first real clue that a supermassive black hole, later named Sagittarius A, was hiding at the heart of our galaxy. Things took a giant leap forward in 1990 when the Hubble Space Telescope was launched into orbit. This powerful telescope allowed astronomers to look at the centers of galaxies with much more detail than ever before. In 1994, one of its instruments, called the Faint Object Spectrograph, observed Messier 87 again. This time it showed that gas near the center was spinning incredibly fast, about 500 kilometers per second, around a very small area. The only explanation was a mass of nearly 2.5 billion suns packed into an area smaller than 1/4 of an arcsecond across. This was some of the strongest evidence yet for a supermassive black hole. In 1995, a team led by Miyoshi used another amazing instrument called the Very Long Baseline Array to look at Messier 106. They studied radio waves from water molecules, called an H2O maser, and found that the signal came from a disk of gas spinning around a compact object with the mass of about 36 million suns. The space was so small, just over 1/10 of a parsec across, that a crowd of smaller black holes couldn't possibly fit without crashing into each other. So again, the only realistic explanation was a single, supermassive black hole. Another big discovery around the same time was made in the galaxy MCG-6-30-15. Scientists found a special kind of X-ray signal called the iron K-alpha emission line. This signal was stretched out and distorted in a way that showed it came from very close to a black hole, just 3 to 10 times the black hole's event horizon. This confirmed how incredibly powerful and strange these objects really are. Then, on April 10th of the year 2019, something historic happened. The Event Horizon Telescope team released the very first picture of a black hole. It showed the huge black hole at the centre of the galaxy Messier 87, giving the world a glimpse of what was once purely theoretical. A year later, in March of 2020, scientists suggested that more rings of light might be found around that image, known as photon rings, which could help us understand even more about these mysterious giants. Even today, the question of where these supermassive black holes originally came from is still being studied. Scientists know they grow by pulling in gas, dust, and even other black holes. But how the very first ones, called seeds, formed is still not fully understood. Some theories suggest that they might have started from black holes that were just a few dozen or a few hundred times the mass of the Sun, created by exploding stars. Over time, these could have grown larger by feeding on surrounding material. Others think these seeds might have formed in a different way. In the early universe, before stars even existed, giant clouds of gas might have collapsed directly into something called a quasi-star, which then collapsed into a black hole about 20 times the mass of the Sun. Or maybe dark matter helped pull in huge amounts of gas, forming supermassive stars that were tens of thousands of times more massive than the Sun, which then collapsed into black holes. There's even a newer idea suggesting that right after the universe began, giant stars, each with a mass of about 100,000 suns, collapsed into black holes, becoming the seeds of the monsters we see today. Some rare theories go even further, proposing that the universe didn't begin with the Big Bang at all, but with something called the Big Bounce. If that were true, then maybe some supermassive black holes are older than the universe we live in now, having existed even before the last cosmic cycle ended. In the very early universe, huge clouds of gas floated around far away in both space and time. These clouds were made of pure, untouched hydrogen and helium, what scientists call metal-free gas. When these clouds were hit by strong light known as Lyman-Werner radiation, something strange happened. Instead of cooling down and breaking apart into smaller clumps, which usually leads to star formation, they stayed together. This was because the light stopped them from cooling, and gravity pulled everything inward, causing the entire cloud to collapse into a single, massive object. As this object collapsed, the pressure and density in the center became incredibly high, about 10 million grams in every cubic centimeter. That's unimaginably dense. At this point, the object could no longer hold itself together. It didn't become a star or even a quasi-star, a short-lived star-like object. Instead, it collapsed directly into a black hole. These massive objects are called direct collapse black holes, and they usually weigh about 100,000 times more than our Sun. In the year 2022, a computer simulation gave us more clues about how the very first supermassive black holes may have formed. According to this simulation, rare chaotic clouds of gas, called primordial halos, were fed by unusually strong streams of cold gas. These cold streams kept new stars from forming too early, which allowed gravity to keep building up pressure. Eventually, gravity won out, and the cloud collapsed into not just one, but two massive black holes. These two black holes had masses of 31,000 and 40,000 times that of the Sun. This showed scientists that the formation of early supermassive black holes might have come from the normal processes of galaxy formation in the young universe. But there's another idea too: primordial black holes. These might have been created just moments after the Big Bang itself. If true, these black holes would have had much more time than other types to grow by pulling in matter. This could explain how some black holes reach supermassive sizes so early. Meanwhile, we already know that many black holes were born from the deaths of the first stars, and scientists have strong evidence to support this. The other theories mentioned above are mostly based on computer models and calculations. To create a supermassive black hole, you need a small area packed with an enormous amount of matter that isn't spinning too fast. Usually, matter in space has a lot of spin, or what scientists call angular momentum, and it takes time for this spin to be pushed outward during the process of accretion, when gas and dust fall into a black hole. This spinning motion is actually one of the biggest things slowing down black hole growth. Accretion is not only the fastest but also the most noticeable way that black holes gain mass. In fact, most of a supermassive black hole's growth happens during periods when it's swallowing gas very quickly. These dramatic events are what we see as quasars or active galactic nuclei, which shine brightly from the centers of galaxies. When scientists look far into space, and therefore far back in time, they see that quasars were much more common when the universe was young. This means that many supermassive black holes had already formed and were growing very early in the universe's history. Some incredibly bright quasars have been found that existed when the universe was less than 1 billion years old. This tells us that supermassive black holes had already reached billions of times the mass of the Sun by that time, suggesting they began forming in the first large galaxies. But there's a limit to how big a black hole can grow. According to current theories, the maximum mass for a black hole growing in the usual way, by swallowing gas, is around 50 billion solar masses. Beyond this point, the surrounding gas disk becomes unstable. Instead of feeding the black hole, the gas starts turning into stars that orbit it. The slowdown in growth starts when a black hole reaches about 10 billion solar masses, and past that it becomes much harder for it to grow. However, in extreme cases, scientists believe it might be possible for a black hole to grow as large as 270 billion solar masses. This would require the black hole to be spinning at nearly its maximum possible speed. Even so, the true upper limit of spin is slightly below the theoretical maximum. Near this maximum mass, something strange happens. The inner part of the disk around the black hole, the innermost stable orbit, becomes larger than the region where the black hole's own gravity dominates. When that happens, the disk can no longer form properly, and the black hole can't grow through accretion anymore. Also, reaching such extreme sizes is very unlikely. To grow that big, a black hole would need to be constantly spinning in the same direction as the material falling into it. But in reality, the material in space often falls in from random directions. This randomness, called chaotic accretion, means that black holes often get pushed in both directions. Sometimes they spin faster, and sometimes they slow down. Over time, these changes tend to slow the black hole's spin more than speed it up. There's more. Black holes also grow by merging with other black holes, but mergers too usually end up decreasing the overall spin. All of these effects combined make it very rare for a black hole to grow beyond about 50 billion times the mass of the Sun, especially if it doesn't spin very fast. Only in rare cosmic situations do black holes even approach that massive limit. Even though modern ultramassive black holes, known as UMBHs, found in quasars and at the centers of galaxies can't grow larger than about 5 to 27 times 10 billion times the mass of our Sun, at least not through their surrounding disks of falling matter, and especially not given the current age of the universe. Some scientists believe that these cosmic giants might still continue to grow far into the future. In fact, in the very distant future, during the slow collapse of vast groups of galaxies called superclusters, some of these black holes might reach almost unbelievably huge sizes, up to 100 trillion times the mass of the Sun. These enormous black holes play a powerful role in the universe. The strong gravity at the center of many galaxies, where supermassive black holes sit, is thought to be the driving force behind some of the most energetic objects in the cosmos, like Seyfert galaxies and quasars. Interestingly, the size of a black hole at the center of a galaxy often matches the size and mass of the galaxy itself, but this connection changes depending on the kind of galaxy we're looking at. There's even a special link known as the M-sigma relation, which connects the mass of a black hole to how fast the stars in the galaxy's central bulge are moving. Faster star motion usually means a heavier black hole. When scientists talk about an AGN, or active galactic nucleus, they mean a galaxy center that holds a supermassive black hole actively pulling in matter. This process gives off a lot of light, making the core extremely bright. Our own Milky Way's centre, however, isn't quite bright enough to be called an AGN. To explain the many different types of AGNs, astronomers came up with a unified model. This model suggests that the differences we observe mostly come from just a few factors, like how bright the AGN is and what angle we're viewing the black hole's surrounding material from. There are two main types of AGNs. One type mainly shines by giving off light through a thick disk of matter swirling into the black hole, while the other blasts out powerful jets of energy moving close to the speed of light, shooting out from the black hole's poles. When two galaxies, each with their own supermassive black hole, collide and merge, the black holes don't just stay where they are. Because of something called dynamical friction, these black holes slowly drift toward the center of the newly formed galaxy. Eventually they get close enough, less than 1,000 parsecs apart, to form a pair. As they continue to interact with the surrounding stars and gas, they spiral even closer together, becoming a tightly bound binary system with a gap of just 10 parsecs or less. If they get within just 1,000th of a parsec of each other, the energy released as gravitational waves will finally cause them to merge into one single massive black hole. After this dramatic collision, the galaxy that formed from the merger will have already settled down, and any initial star-forming fireworks or AGN activity will have faded. But the black hole merger leaves behind something else, a powerful blast of gravitational waves. These waves can give the resulting black hole a giant kick, pushing it through space at thousands of kilometers per second. In some cases, the kick is strong enough to knock the black hole right out of the galaxy. This strange event is known as a gravitational recoil. There's another way a black hole can be thrown out of a galaxy. Imagine two galaxies merging, forming a pair of black holes. Then a third galaxy joins the mix, adding yet another black hole to the center. When three black holes interact, things can get chaotic. Usually the lightest of the three is flung out into space, while the other two shoot off in the opposite direction as a new binary pair. This kind of three-body gravitational dance is called the slingshot recoil. Any of the three black holes can end up being ejected, and those that get thrown out into space are called runaway black holes. Astronomers have found several clues that might point to such recoiling black holes. For example, if a bright AGN or quasar is not in the middle of a galaxy where we'd expect it to be, that could be a sign. Or if we find two different light signatures coming from one quasar, it might be a hint that there's a black hole being flung away. Some possible examples of recoiling black holes are in galaxies like NGC 3718, SDSS 1133, 3C186, E1821 plus 643, and SDSS J 0927 plus 2943. As for potential runaway black holes, they might include He 0450-2958, CID42, and objects near the dwarf galaxy RCP-28. Runaway black holes can leave behind a trail of star formation as they move. In fact, a straight line of newly born stars near RCP-28 was once thought to be the wake left by a runaway black hole, but later research suggested that the feature might just be a small galaxy seen from the side without a central bulge. And there's a fascinating process called Hawking radiation, named after the famous physicist Stephen Hawking. According to quantum theory, black holes aren't completely black. They slowly give off tiny amounts of heat energy due to strange effects near their edges, called event horizons. This process gradually shrinks the black hole, and if left alone for long enough, it would eventually cause it to disappear completely. For example, if there were a black hole 100 billion times heavier than the Sun, it would take about 2.1 times 10 to the power of 100 years to vanish. And if we imagine an even bigger black hole, one formed during the collapse of a supercluster in the far future, with a mass of 100 trillion suns, it could take about 2.1 times 10 to the power of 1009 years to fully evaporate. Some of the strongest clues that black holes really exist come from a phenomenon known as the Doppler effect. This is the same effect that makes a siren sound different as it moves past you. In space, it affects light. When matter is moving away from us, its light becomes redder, a process called red shifting. When matter is moving toward us, the light becomes bluer, or blue shifted. Near a black hole, things get really extreme. The matter that orbits close to a black hole has to move incredibly fast, almost as fast as light itself. Because of this, the part of the matter moving away from us appears much fainter, while the part moving toward us looks much brighter. This makes something that is actually evenly shaped, like a ring or disk of matter, look completely uneven and distorted to our eyes. Modern computer-generated images of black holes take this effect into account. One famous example shows what the black hole at the centre of our own galaxy, the Milky Way, might look like. This black hole is called Sagittarius A star, and it's based on a scientific model that many experts believe is very accurate. However, our current telescopes still aren't sharp enough to see this level of detail directly, so we rely on simulations for now. Still, scientists have been able to observe something else, matter swirling around farther out from what we believe are black holes. This matter moves much slower than light, which makes it easier to measure. For example, water molecules in space can emit very specific radio signals called masers, which are similar to lasers but with microwaves instead of light. By studying these masers in galaxies near us, scientists have seen very fast Keplerian motion, meaning the matter is moving in the way predicted by Kepler's laws of planetary motion. This only happens when an enormous amount of mass is packed into a tiny area, something only black holes, or soon-to-be black holes, can explain. For galaxies that are farther away, astronomers can study the width of certain light signals, called broad spectral lines, which gives clues about gas orbiting near the black hole's event horizon, the point of no return. One advanced method, called reverberation mapping, looks at how these light signals change over time to estimate both the black hole's mass and, possibly, how fast it's spinning. There is strong evidence that our own Milky Way galaxy has a supermassive black hole at its core, about 26,000 light-years from the solar system. This region is known as Sagittarius A star. Scientists have studied a star called S2, which moves in a stretched-out, oval-shaped orbit around this mysterious object. It takes about 15 years and 2 months for S2 to complete one full orbit, and it gets as close as 17 light-hours, that's about 120 times the distance between the Earth and the Sun, to the centre of the black hole. From how S2 moves, scientists have estimated that the central object must have a mass of about 4 million times the mass of our Sun. Yet, it must fit into a space no larger than 17 light-hours across. Otherwise, S2 would crash into it. Another star, S14, has helped show that this mysterious object is even smaller, with a radius of less than 6 1/4 light-hours, roughly the size of Uranus's orbit around the Sun. No other known object in the universe, except a black hole, could be this massive and compact. Even more fascinating are the infrared observations of bright flares coming from Sagittarius A star. These show a kind of glowing plasma, hot, charged gas, orbiting incredibly fast, about 30% the speed of light, in tight circles just outside the black hole's point of no return. These flares seem to come from a superheated hot spot on the accretion disk, the spinning disk of matter falling into the black hole. This hotspot appears to follow a circular orbit within a strong magnetic field. On January 5, 2015, NASA observed an X-ray flare from Sagittarius A star that was 400 times brighter than usual, a record-breaking event. Scientists believe this might have been caused either by an asteroid being torn apart as it fell into the black hole, or by magnetic fields twisting and snapping inside the swirling gas. So far, we have rock-solid proof of supermassive black holes in only a few galaxies. These include our Milky Way, the Andromeda Galaxy, also known as M31, a smaller companion galaxy called M32, and a few others outside our local group, like NGC 4395. In these galaxies, the speeds of stars or gas near the centre rise dramatically as you move closer inward, which matches what you'd expect if a massive object, a black hole, was pulling them in. In most other galaxies we've observed, these speeds don't rise the same way, so we can't say for sure whether a black hole is there or not. Still, most astronomers believe that nearly every galaxy has a supermassive black hole at its centre. This belief comes from something called the M-sigma relation. In simple terms, this means there is a strong link between the mass of a galaxy's central black hole and how fast the stars in the galaxy's bulge are moving around. This pattern has been seen in about 10 galaxies, where we have very accurate measurements, and it suggests that galaxies and their black holes might grow and evolve together. On March 28, 2011, astronomers witnessed something incredible: a supermassive black hole ripping a mid-sized star apart. They saw a sudden burst of X-rays and other signals, and the only explanation that fits is that a star got too close and was torn apart by the black hole's gravity. This happened in a galaxy where the central black hole had been quiet until then. Based on what was seen, scientists think the black hole had a mass of around 1 million times that of the Sun. The event also created powerful jets of material blasting out at high speeds, almost as fast as light, something called a relativistic outflow. A large part of the star likely fell into the black hole, and future observations will help confirm this theory by studying how the light fades over time. The Andromeda Galaxy, which is about 2.5 million light-years from Earth, contains a central black hole about 140 million times the mass of the Sun, much bigger than the one in the Milky Way. An even more massive black hole lives in the giant galaxy Messier 87, located around 48 million light-years away. This black hole is about 6.5 billion solar masses. The largest known black hole in our local region is found in the NGC 4889 galaxy, in the Coma Berenices constellation. It is around 336 million light-years from Earth, and contains a black hole with a mass estimated at 21 billion times the Sun's mass. When it comes to quasars, extremely bright and distant objects powered by black holes, we use indirect methods to guess their black hole masses. These methods are tricky and come with a lot of uncertainty. One extreme example is the quasar Photon 618, which may contain a black hole with a mass of about 40.7 billion times that of the Sun. Its light comes from a time when the universe was still young, with a redshift of 2.219. Other quasars with massive black holes include APM 08279 plus 5255, with about 10 billion solar masses, and SMSS J 2157 28.21-360215.1, with about 34 billion solar masses, almost 10,000 times bigger than the Milky Way's central black hole. Some galaxies appear to have two supermassive black holes at their centres, forming a pair. If these black holes were to collide, the event would create powerful gravitational waves. This kind of binary system of supermassive black holes is believed to be a common result of galaxies merging. One well-known example is the binary pair in the galaxy OJ 287, which is located 3.5 billion light-years away. This pair contains the most massive black hole ever discovered in such a system, with a mass estimated at 18 billion times the mass of the Sun. In 2011, a supermassive black hole was found in the small galaxy Henneis 210, which does not have a bulge. The exact implications of this discovery on the formation of black holes are still unclear, but it might suggest that black holes could have formed before the bulges in galaxies. In 2012, astronomers made another surprising discovery when they found a black hole in the galaxy NGC 1277, which is located 220 million light-years away in the Perseus constellation. This black hole was reported to have an unusually large mass of about 17 billion times the mass of the Sun. This mass is roughly 59% of the mass of the galaxy's bulge, which makes up 14% of the galaxy's total stellar mass. However, other research suggested a different result. The black hole might not be that massive, with an estimated mass ranging from 2 billion to 5 billion times the mass of the Sun, with 5 billion being the most likely value. On February 28, 2013, astronomers used the NuSTAR satellite to measure the spin of a supermassive black hole for the first time. The black hole they studied was in the galaxy NGC 1365, and they found that its event horizon was spinning almost as fast as the speed of light. In September 2014, data from various X-ray telescopes revealed that the very small, dense and ultra-compact galaxy M60 UCD1 contains a black hole at its centre, with a mass of 20 million times the mass of the Sun. This black hole makes up more than 10% of the total mass of the galaxy. This discovery was surprising because this black hole is 5 times more massive than the one at the centre of our Milky Way galaxy, even though M60 UCD1 is less than 5,000ths the mass of the Milky Way. Some galaxies do not have supermassive black holes at their centres. While most galaxies without a supermassive black hole are small dwarf galaxies, one case remains puzzling. The supergiant elliptical galaxy A 2261 BCG, which is one of the largest known galaxies, has not been found to contain an active supermassive black hole with a mass of at least 10 billion times the mass of the Sun, even though it is over 6 times the size and 1,000 times the mass of the Milky Way. However, several studies have suggested that the possible black hole at its centre could have a mass anywhere between 6 billion and 10 billion times the mass of the Sun. This suggests that the galaxy might either have a black hole that is not actively growing, or one that is smaller than 10 billion times the mass of the Sun. In December 2017, astronomers reported the discovery of the most distant quasar ever found at that time, Ulysses J 1342 + 0928, which contains the farthest supermassive black hole, with a redshift of 7.54. This surpassed the previous record held by the quasar Ulysses J 1120 + 0641, which had a redshift of 7. In February 2020, astronomers announced the discovery of an eruption in the Ophiuchus supercluster, which was the most energetic event ever detected in the universe since the Big Bang. This event took place in the Ophiuchus cluster, specifically in the galaxy Neve 1, where nearly 270 million times the mass of the Sun's material was being pulled into its central supermassive black hole, which has a mass of 7 billion times the Sun's mass. The eruption lasted around 100 million years and released 5 million times more energy than the most powerful gamma-ray burst ever observed. The eruption produced shock waves and jets of high-energy particles that expanded into the surrounding space, creating a massive cavity about 1.5 million light-years wide, which is 10 times the diameter of the Milky Way. In the month of February in the year 2021, a team of astronomers made an incredible announcement. They had created one of the most detailed images of the universe ever seen, an image that revealed the locations of about 25,000 active supermassive black holes. These are not just ordinary black holes, but the giant ones that lie at the hearts of galaxies, each one millions or even billions of times heavier than our Sun. What made this image so special was not just the number of black holes it showed, but the way it was made. It covered around 4% of the northern part of the sky, known as the Northern Celestial Hemisphere. That may sound small, but in the vastness of space, it's still a huge area filled with cosmic wonders. To see these invisible giants, astronomers used a powerful tool called the Low Frequency Array, or LOFAR for short. This is a network of radio telescopes spread across several countries in Europe. LOFAR doesn't look at the sky the way our eyes do. Instead, it listens to the universe using very low-frequency radio waves, signals that are far below what the human ear could ever hear. These waves are perfect for spotting the powerful jets and energy bursts coming from black holes that are devouring matter. Black holes come in many different sizes, and one of the most mysterious types is known as the intermediate mass black hole, often shortened to IMBH. These black holes are not small, but they're not the biggest either. They fall right in the middle. Their weight ranges from around 100 times the mass of our Sun to as much as 100,000 suns. That's much heavier than the usual black holes that are formed when giant stars die, called stellar black holes, but they're still much smaller than the supermassive black holes found at the centres of galaxies, which can weigh more than 1 billion suns. Over the years, scientists have found a few possible examples of these medium-sized black holes, both in our own galaxy, the Milky Way, and in other galaxies nearby. Interestingly, they didn't actually see these black holes directly. Instead, they studied how gas clouds around them were moving, or they observed the light coming from the accretion disk, a spinning disk of superheated material that forms when a black hole pulls in matter. These clues gave scientists reason to believe that intermediate mass black holes might be hiding in those places. One of the most thrilling discoveries related to IMBHs came from a ripple in space-time itself. On the 21st of May 2019, at exactly 3 minutes and 2 seconds past 3 in the morning Coordinated Universal Time, scientists detected a powerful gravitational wave signal, which they named GW 190521. This cosmic wave was caused by two black holes colliding with each other. One weighed about 85 times as much as the Sun, and the other about 65 suns. When they crashed, they formed a new black hole with a mass of 142 suns. The difference, about 8 solar masses, was released as gravitational waves during this enormous explosion in space. This amazing event was officially shared with the world on the 2nd of September, 2020. Before this, the best hints of IMBHs came from certain galaxies called low-luminosity active galactic nuclei. These galaxies glow faintly, and their strange behavior makes scientists think there might be black holes inside them. In some cases, astronomers could even estimate the size of the black holes using a special technique known as reverberation mapping, which looks at how light echoes off gas near the black hole. One good example is the spiral galaxy called NGC 4395, which is located about 4 million parsecs away from us. In the center of this galaxy, there seems to be a black hole that weighs around 360,000 solar masses. A huge group of possible intermediate mass black holes, exactly 305, was discovered after a deep study of about 1 million galaxy light readings. This data came from a large project called the Sloan Digital Sky Survey. Out of those 305, 10 were found to be giving off X-rays, which helped confirm that they might really be black holes of intermediate size. Another interesting place to look for IMBHs is in mysterious objects called ultra-luminous X-ray sources, or ULXs. These are incredibly bright spots in the X-ray sky, and they often show up in galaxies where new stars are being born, like the famous starburst galaxy M82. ULX are usually located near groups of young stars, and scientists think that they might be black holes feeding on nearby stars. But to really prove that there's an IMBH there, astronomers need to carefully examine the light from the companion star and track its movement. Some researchers believe that IMBHs might also be hiding in globular clusters. These are tight, round groups of stars that orbit around galaxies like the Milky Way. To search for black holes in these clusters, scientists measure how the stars at the center are moving. If something supermassive is lurking there, it should disturb the motion of nearby stars. However, so far, none of the supposed discoveries have stood up to further examination. One example is a cluster named M31G1. At first, it looked like it might contain a big black hole, but later studies showed that the data could be explained without needing one at all. Gravitational waves might hold the key to solving this cosmic puzzle. If an intermediate mass black hole teams up with another black hole, or even a dense object like a neutron star, their spiraling motion as they move closer together would send out ripples in space-time. These ripples could be detected by powerful instruments like LIGO and Virgo. There's also a mathematical rule known as the M-sigma relation, which helps predict how large a black hole should be based on how stars move around the center of a galaxy. According to this rule, smaller galaxies with dimmer centers are expected to have black holes that weigh between 10,000 and 1 million times the mass of the Sun. The smallest black hole ever predicted using this method is found in a galaxy called RGG 118, and it weighs just around 50,000 solar masses. Back in November of the year 2004, astronomers announced something remarkable. They had found what they believed to be the first intermediate mass black hole in the Milky Way. This black hole was named GCRs 13e, and it weighs about 1,300 solar masses. It is located just 3 light-years away from the Milky Way's enormous central black hole. Sagittarius A GCRs 13e is part of a group of 7 stars, which might be what's left of a much larger star cluster that was torn apart by the powerful gravity near the galaxy's core. This finding supported the idea that supermassive black holes might grow by gradually swallowing smaller black holes and stars. However, not everyone agreed. In the following year, 2005, a German team of scientists raised doubts. They studied the way the stars in that cluster were moving and suggested that there might not be a black hole there after all. If an IMBH really is orbiting close to the center of our galaxy, it might be possible to catch it by watching how it affects the motion of the stars nearby. Then, in January of 2006, a team led by Philip Carrett from the University of Iowa made another exciting announcement. They found a repeating signal, called a quasi-periodic oscillation, coming from a possible black hole in galaxy M82. This object, named M82 X-1, appears to be feeding on a red giant star, which is slowly losing its outer layers. The discovery was made using a special satellite called NASA's Rossi X-ray Timing Explorer, but even this discovery wasn't fully accepted. The signal only went through about 4 cycles, which might not be enough to prove that it was truly repeating. It could just be random background noise. And even if the signal is real, scientists still don't know if it's caused by the star's orbit or by a slower process happening in the black hole's accretion disk. In the year 2009, astronomer Sean Farrell and his team made yet another breakthrough. They discovered a strange object named HLX-1, which turned out to be an intermediate mass black hole. What made HLX-1 so fascinating was that it appeared to be surrounded by a small bunch of stars, almost like a tiny galaxy of its own. HLX-1 was found inside a larger galaxy called ESO 24349, and the scientists believed that this galaxy had once collided with a smaller galaxy that carried HLX-1. Most of the smaller galaxy's stars were absorbed, but the black hole remained. A few years later, on the 9th of July 2012, scientists using a radio telescope operated by CSIRO in Australia announced another major finding. They believed they had discovered the first clear example of an intermediate mass black hole based on strong radio evidence. Then, in the year 2015, researchers at Keio University in Japan made a surprising observation. They were studying a strange gas cloud known as CO0.400.22, and they noticed that the gas particles were moving at extremely different speeds. After running simulations on a computer, they concluded that the best explanation was the presence of a black hole weighing around 100,000 times as much as our Sun. But even this wasn't a sure thing. Later studies suggested that the behavior of the gas cloud might also be caused by shock waves from exploding stars known as supernovae. So the mystery continues. Back in the year 2017, scientists thought they had made an exciting discovery. They believed they had found a black hole hiding deep inside a giant ball of stars known as a globular cluster. This cluster is called 47 Tucanae and is located in the southern sky. The black hole they suspected was not like the usual small ones formed when massive stars die. Instead, it seemed to be a mysterious in-between type called an intermediate mass black hole, possibly weighing a few thousand times more than our Sun. This idea came from looking at the way special spinning stars called pulsars were moving. Their speed and direction hinted that something very heavy might be pulling on them. But when more precise observations were made later, scientists could not find solid proof of any black hole there after all. Then came the year 2018, and once again, scientists from Keio University in Japan were in the spotlight. This time, they discovered several streams of cold gas circling around something invisible, located close to the center of our Milky Way galaxy. This hidden object, which had the technical name HCN 0.0090.044, was estimated to have the mass of about 32,000 suns. If confirmed, it would become the third known black hole in that puzzling middle range of mass, too big to be born from a single star, yet not large enough to be considered supermassive. Just a year later, in 2019, a dramatic cosmic event caught scientists' attention. They detected something called gravitational waves, ripples in space and time, caused by the collision of 2 black holes. One of these black holes had a mass about 66 times that of the Sun, while the other was even bigger, about 85 times the Sun's mass. When they smashed into each other, they merged into a brand new black hole that was roughly 142 times heavier than the Sun. Around 9 solar masses worth of energy was released in the form of gravitational waves. This massive event, named GW 190521, added another important clue in the search for medium-sized black holes. In the year 2020, astronomers may have found another one of these mysterious objects. They discovered a possible black hole with the complex name 3XMMJ 215022.4055108. This candidate lies in the direction of the Aquarius constellation and is estimated to be around 740 million light-years away from Earth. Once again, it could be an intermediate mass black hole. The very next year, in 2021, came another exciting announcement. scientists reported finding a black hole that seemed to weigh around 100,000 times the mass of our Sun. This one was located inside a globular cluster called B023G78, which lies in the Andromeda Galaxy. Although the discovery was first shared as a scientific preprint, it quickly gained attention from researchers around the world. Then, in the year 2023, astronomers took a closer look at Messier 4, the closest globular cluster to Earth. They noticed that the stars in this cluster were behaving strangely, as if something very heavy and compact was sitting at its centre. The mysterious object seemed to be about 800 times heavier than our Sun. Because it was so tightly packed and didn't spread out like a group of stars normally would, scientists suspected it might be a black hole. Still, they couldn't be completely sure. It might also be a bunch of white dwarfs, neutron stars, or small black holes clustered together. On the 10th of July in the year 2024, another intriguing study made headlines. This one focused on 7 stars in a cluster called Omega Centauri. These stars were moving very fast, in a way that suggested they were orbiting something heavy and invisible. The researchers estimated that this hidden object had a mass of at least 8,200 times that of our Sun, making it another strong candidate for an intermediate mass black hole. But here's where things get really puzzling. These middle-sized black holes don't seem to follow the usual rules. They are too massive to form the way smaller black holes do, which usually happens when a single star explodes in a supernova and collapses. Yet they are also too small to form the way supermassive black holes do, those giants that live in the crowded high-energy centres of galaxies. So how exactly do intermediate mass black holes come into existence? Scientists have a few possible explanations. One idea is that many smaller black holes, over millions or even billions of years, slowly merge together to form a larger one. Another theory is that, in very dense clusters of stars, several huge stars might crash into each other. The final result would be a massive merged star that could then collapse into an intermediate black hole. A more exotic theory suggests these mysterious black holes might have formed shortly after the universe began, soon after the Big Bang, making them what scientists call primordial black holes. There's also an ongoing debate about whether a single, enormous star could collapse directly into an intermediate black hole. For this to happen, the star would need to be incredibly massive, at least 260 times heavier than our Sun. Some scientists think this could happen if several stars in a young, crowded cluster merged into one gigantic star. If that giant star then collapsed, it might create an intermediate mass black hole. But events like this would be extremely rare and hard to catch in action, making them one of the universe's best-kept secrets. A binary black hole, also known as a black hole binary, is like a cosmic couple, a pair of black holes locked in a powerful gravitational dance around each other in space. Imagine 2 invisible giants, circling one another in a quiet but intense waltz, hidden deep in the darkness of the universe. These strange duos come in 2 main types. The first kind is called binary stellar mass black holes. These are born when 2 huge stars, far more massive than our Sun, live and die together. When both stars explode and collapse under their own gravity, they can turn into black holes. If they were orbiting each other before, they might continue orbiting after becoming black holes. Sometimes, 2 black holes that were not born together might wander close enough in space to become locked in an orbit, forming a binary system. The second type is far bigger and even more mysterious. Binary supermassive black holes. These form when 2 entire galaxies collide. Each galaxy usually has a giant black hole at its centre, and when the galaxies crash together, their central black holes slowly drift closer over time. Eventually they may end up orbiting each other, like a heavyweight version of the stellar ones. For many decades, scientists had only guesses and indirect clues about binary black holes. Black holes are extremely hard to detect because they don't emit any light. They're like cosmic ghosts, powerful but invisible. Also, the scientific tools we had weren't sensitive enough to spot them directly. But there was one powerful hint. When 2 black holes merge, they send out a massive burst of energy. Not in the form of light or sound, but as gravitational waves, tiny ripples that stretch and squeeze space-time itself, like ripples in a pond after you drop a stone. These waves were predicted by Albert Einstein way back in the early 20th century in his famous theory of general relativity. He even described the unique patterns, called waveforms, these ripples would make. By the late 20th century and early 21st century, scientists were eager to find solid evidence. They believed that the best way to prove gravitational waves existed was to catch them coming from a pair of black holes spiraling into one another. Such a merger would produce one of the loudest gravitational signals in the whole universe. As two black holes orbit, they give off gravitational waves, which slowly drain away their energy. This causes them to spiral in closer and closer, moving faster and faster. This stage is called the inspiral. Eventually they collide in a violent merger and become one larger black hole. After that, the new black hole goes through a phase called the ringdown, where it settles into a smooth, stable shape, releasing leftover gravitational waves as it does. Right before they merge, the two black holes reach astonishing speeds, and the energy released in gravitational waves peaks in that final split second. On the 14th of September in the year 2015, something incredible happened. A massive scientific instrument called LIGO detected a signal. This signal was named GW150914. What LIGO had discovered was the sound of two black holes merging over 1,300,000,000 light-years away. Each of these black holes was about 30 times heavier than our Sun, and when they crashed into one another, they released energy equal to about 3 solar masses, turned entirely into gravitational waves. This energy burst reached a peak of around 3.6 times 10 to the power of 49 watts, more than all the stars in the visible universe combined at that moment. The official announcement of this discovery came in February of the year 2016, and it was the first solid proof that binary black holes and gravitational waves were real. Since then, scientists have detected many more mergers involving stellar mass black holes, but finding clear evidence of supermassive black hole binaries has been much harder. Some galaxies, such as NGC 6240, show two bright centers that might hint at two supermassive black holes still drifting toward one another. Others, like SDSS J 104807.74 plus 005543.5 and EGSD2 J 142033.6652 5917.5, give off strange light signals that could be signs of two supermassive black holes orbiting tightly together. In other galaxies, the light coming from the center pulses in a repeating pattern, like a beating heart. This may be caused by one supermassive black hole circling another. A well-known example is the galaxy OJ287. Then there's the curious case of galaxy J0437 plus 2456, where a supermassive black hole seems to be moving oddly. Some scientists think it might be getting pushed by another black hole nearby, or even recoiling after a recent cosmic collision. Another fascinating object is a quasar named PKS 1302-102, where scientists believe two black holes are orbiting each other with a rhythm of about 1,900 days. When two galaxies merge, their central black holes usually don't collide right away. Instead, they swing past each other in wide loops like dancers missing each other's arms. Something needs to slow them down so they can finally come together. This slowing down is helped by a process called dynamical friction. As a black hole moves through space full of stars, its gravity pulls on them, stealing energy and slowing it down. Eventually, the black holes may get within just a few parsecs of each other. But here's the tricky part. Once they get that close, they've already cleared away most of the nearby stars and gas. With nothing left to slow them down, their orbits might stall, remaining stuck for a time longer than the age of the universe. This is called the final parsec problem, figuring out how black holes can close that last little gap. Luckily, when the black holes get really close, within just a few thousandths of a parsec, gravitational waves finally take over. These waves steal energy quickly and send the black holes on a direct path to a powerful merger. To help black holes get through the final parsec, scientists have come up with clever ideas. One is to bring in extra matter, like stars or gas clouds, which can tug on the black holes and help them lose energy. Some researchers are even considering dark matter, but it would need to be a special kind that can interact with itself, or else it would fly away too fast to help. Another rare but helpful situation is when a third supermassive black hole enters the picture, maybe because of a second galaxy crashing into the first. These three black holes can bounce off each other in wild and chaotic ways, giving them more chances to lose energy and spiral together. This chaos also stretches their orbits, making their gravitational waves stronger whenever they swing close. To truly understand how black holes orbit and merge, scientists use advanced math and powerful computers. In the early stages, they use something called post-Newtonian approximations, which are like building blocks of Newton's laws with extra layers from Einstein's theory. They also use a smart method called the effective one-body approach, which turns the two-body problem into a one-body problem to make it easier to solve, especially when one black hole is much larger than the other. After the merger, during ringdown, scientists use perturbation theory to calculate how the new black hole vibrates. It usually forms what's called a Kerr black hole, which spins, and its ringing gives off special patterns of gravitational waves. To simulate the entire process from beginning to end, scientists rely on a field called numerical relativity. This uses supercomputers to model the swirling dance of space and time as black holes spiral in and collide.